Thank you very much. So great pleasure to be here. It's actually my second time in Kraków, and I think it's a very beautiful choice for having a machine learning summer school. So in the next 3 hours, I would like to talk about geometric deep learning, and if you wonder this intriguing image, what does it have to do with machine learning? So you see, it fits more a kind of an alchemist. So we wanted to use this image in reference to this famous quote from Ali Rahimi, who was receiving the Best Paper Award or the Proof of Time Award at NeurIPS in 2017. And he was speaking this way, maybe a little bit critically about deep learning, at least at that time, that we say things like machine learning is the new electricity, and his alternative metaphor was machine learning has become alchemy. So in the sense that some kind of science that maybe produces something that we don't really understand what it does. And really what we would like to do here is to try to understand from certain perspective how these methods work and why they work, and maybe more importantly, when they fail. And you see kind of maybe general blueprint for developing potentially future machine learning systems. So the concept that will be important to these lectures is the concept of symmetry. And symmetry, according to Weil, whom I'm quoting here, is, depending on how wide or narrow you define its meaning, is an idea by which man, through the ages, has tried to comprehend and create order, beauty, and perfection. So it sounds a bit poetic, but I think it is true. So that's from his book that is titled Symmetry, that he published in Princeton. And symmetry is a Greek word, so it goes back to the ancient Greeks. And as you probably know, ancient Greeks like Plato considered symmetry to be really the cornerstone of the universe. So according to Plato, what is nowadays called Platonic solids, symmetric polyhedra, were the basic building blocks of all the stuff in the universe. So probably tiny little things that build up the matter. And if you think of it in modern terminology, that's not very far from truth. So Plato believed that geometry is really the key piece of mathematics, and even according to a legend, there was an inscription on the entrance to his academy saying that nobody skilled in geometry, that is not skilled in geometry, should be allowed to enter. And this idea of matter being built of small symmetric polyhedra actually not far from truth if you consider how crystals are organized. And the first to study this from a formal perspective was actually Kepler, who is maybe more famous for his discovery of the motion of planets, but he was also the one who laid the foundations of modern crystallography, basically considering how spheres can be packed into different configurations. And if you also think that this is an old and boring and outdated stuff, so last year's Fields Medal was given exactly for solving these kind of problems, maybe in higher dimensions. So geometry itself also, at least in formal way, goes back to ancient Greeks, and what we still often study at school as the geometry dates back to Euclid, his famous elements, so a system of axioms from which his geometry was derived. And as you know, there are 5 axioms or 5 postulates of Euclidean geometry that the last one was somehow standing out, and people for many centuries or even thousands of years tried to do something with it. And for example, in the 18th century, Giovanni Saccheri, who was a priest, almost arrived to the construction of a non-Euclidean geometry, but he considered it such a heretical idea that he thought that it is repugnant to the nature of straight lines. So he abandoned these ideas and never took it to the full extent. But in the 19th century, what happened is that finally came the realization that dethroned Euclid and broke his monopoly of geometry, and the works that probably Gauss himself did but never published, and then famously Lobachevsky, Boyer, and Riemann, who created the first examples of what we nowadays call non-Euclidean geometries. And in the 19th century, this is how the geometry started looking like. So a zoo of different types of geometry without clear relation or understanding what actually defines in geometry. So there was obviously a need to put order in this mess, and the new idea, new approach came from Felix Klein in 1872. So he was only 23 years old. he was lucky to get an appointment as a professor at the University of Erlangen in Bavaria. So this is something that, for example, Euler failed to have in Switzerland. They had to go to Russia and to become a faculty. Probably not very dissimilar to situations that some of us are facing in these days. So Klein was asked, as it was customary in Germany and still customary, I think, to deliver a research prospectus, basically to explain what he is going to do until his retirement in Erlangen, which actually never happened because he moved 3 years after to different places, eventually to Göttingen. And in this prospectus that entered the history of mathematics as the Erlangen program, he proposed a kind of algebraization of geometry, so studying geometry from the perspective of group theory, so essentially considering a geometry as a space plus some class of transformations formalized using group theory, and studying properties that remain unchanged or invariant under these transformations. So you take an object and you apply to it rigid motions, and you preserve a lot of things like areas, parallel lines, distances. So this is how you create Euclidean geometry. But you can consider other groups, like affine or projective groups. And in fact, he considered projective group to be the broadest construction. He, in fact, showed, together with Beltrami, that the first non-Euclidean geometries, hyperbolic geometries with negative curvature, could be constructed with a projective model. And these ideas had really big impact on geometry, on mathematics more broadly, I would say culturally. Like category theory is an extension of these ideas to more abstract objects. But probably most importantly, it had impact on physics, where came the realization in the beginning of the 19th century, probably starting with Noether with her famous theorem, that the laws of physics themselves can be derived from considerations of invariance or symmetry. And for example, what Noether showed is that principles like conservation of energy that previously were considered to be empirical could be derived mathematically from certain symmetries, so symmetry of time in this case. And these ideas in a more generalized form led to what nowadays is known as the standard model. So basically all the world can be modeled and can be derived from first principles of symmetry. So what I think physicists among you would call external symmetry or internal symmetry, right? The symmetry of the space-time, so what is called the Poincare group that gives rise to Minkowski geometry of special relativity, or internal symmetries of quantum fields. That's what gives rise to different forces or different interactions. And I think nobody put it better than Philip Anderson, Nobel laureate in physics, that with only slightly overstating, you can say that physics is the study of symmetry. So what does it all have to do with deep learning and neural networks and machine learning in general? So let's do maybe a brief detour into the history of machine learning or artificial intelligence, right? So the term artificial intelligence comes from these people. The Dartmouth conference that happened in 1956, organized by McCarthy and others. And you can see them, some very prominent figures sitting here. So this is, for example, this is Claude Shannon, and this is Marvin Minsky, who would become all very important scientists. And historically, apparently, the term artificial intelligence was introduced to kind of distance themselves and not to be in the shadow of the expert of that time, who was Norbert Wiener, who introduced the term cybernetics, which I think is still used. I think here in Poland, it's probably still used as a kind of overarching term for everything that has to do with computer science and artificial intelligence. So around that time, there were many works that try to understand how the brain works. So I think at that time, it was already understood that somehow our intelligence is concentrated in the brain. So models for neural networks, probably the most famous one is by Frank Rosenblatt, the so-called perceptron, but there are models before that. And he was able to show, that was in the 50s, so these models had to be implemented in analog hardware. He was able to show that he can solve some simple pattern recognition problems with these neural networks. And it was extremely remarkable at that time, so there were articles in the popular press like the New Yorker saying that this is the first serious rival to the human brain ever devised, right? So I think you can only smile, I can hear you laughing. And it's remarkable machines capable of what amounts to thought, right? So that's, according to New Yorker, was the perceptron. And there was a little bit of hype, right? As you probably know, this MIT computer vision summer project. So they thought that they would be able to model a large part of the visual system over one summer. Of course, we're still working on these problems 50 years after, and there is no end to it. But also at MIT, these two guys, so one of them appeared already in the picture, Marvin Minsky and Seymour Papert. They published a highly famous, or infamous if you want, book called The Perceptrons, where they introduced mathematical analysis of these networks proposed by Rosenblatt. And they showed, for example, one example that is taken from this book, that a very simple logical function like exclusive OR could not actually be implemented as a perceptron. So these basically these patterns are not linearly separable. So that was very harsh criticism for the models, and some people say in retrospective that this was what triggered the AI winter. So some people even say that there might have been some personal animosity between Rosenblatt and Minsky. They went to the same high school, and Rosenblatt also died in a boating accident. So some were as far as to suggest that it was a suicide. Well, the story is probably much more mundane. So the funding and that was cut by government agencies like DARPA was more related to them being more pragmatic and budget restricted, and that had an impact on the field that coincided with the publication of the book. But if you look at the substance of the problem, what Minsky and Papert called in their book Perceptron was actually not exactly the architecture that was devised by Rosenblatt. So they actually clearly stated. So they refer to this architecture as simpler perceptrons, and this is what we now typically understand by this term. So it's, as you know, it's just a linear combination of the input coordinates with learnable weights that go through a nonlinear activation, typically a sigmoid or in simple case, a sine function. But what is also very important, they were probably the first ones, at least to my knowledge, to use geometric approaches to machine learning problems. So they, for example, formulated this group invariance theorem that tell in which or to what kind of transformations in the input patterns the neural network will be invariant. And another interesting thing, actually, the subtitle of the book is an introduction to computational geometry. So that was the 60s, so this term didn't exist. They actually introduced it, and one of the reviews of the book that was critical was asking whether this is just some kind of new mathematical fad that will go away a few years after. And as you probably know, computational geometry is now a very well-established field, so it has remained there for a long time. But if you go into the substance of the discussion, is actually the question is what kind of classes of functions these neural networks could represent, right? So what is called the expressive power. And there were results at that time, so coming from mathematicians, in particular Kolmogorov and Arnold, working in the Soviet Union, that claim that you can take multidimensional functions and decompose them in this way, and basically any function could be decomposed in this way. So these kind of results are known as universal approximation. They go probably as far as the 13th problem formulated by David Hilbert, and the modern statements of these theorems are usually attributed to Seibenko and Hornig. These are late 80s, early 90s that are specific to deep neural networks. So what these results say is that if you have not a single layer of perceptron, but two layers like this, then you can approximate any continuous function to any desired accuracy. So the results, it's a class of results, it's not a single result, but roughly the way that we can understand it is that with just a configuration like this, with just two neurons like this, you can approximate, you can represent a step function. Once you can represent step functions, you can decompose a continuous function into tiny little steps. So the proof is slightly more involved, but that's roughly the idea. Now, it's not a constructive proof, and there are different versions for limited width or limited depth, and so on. It's not a constructive proof, so it doesn't tell you how. So it's an existence result, right? So it tells you that you can find a neural network with potentially a very large number of neurons that approximate functions. And if you look at machine learning problems, right? So in the very maybe simple and naive setting, like classifying images of cats and dogs, basically you can think of it, some synthesists say that deep learning is a curve fitting problem, right? So it's multidimensional curve fitting. So there is some kind of black box, right, where you put some something that acts as a universal approximator, right? So some sufficiently rich architecture, and you try to represent the function that distinguishes between cats and dogs in this way. Of course, this is not a well-defined problem, right? If I give you a finite sample of, let's say, these are cats and dogs, right? I can pass infinitely many functions through these points, right? So I can interpolate these points in infinitely many ways. So we need somehow to restrict our class of functions, and that's typically what you do by imposing some sort of regularity. And mathematicians have very well understood concepts of regularity, like Lipschitz continuity, right? So in simple case, you can think of it as a function with bounded derivatives, right? And the problem is, what happens when you increase the dimensionality of your input, when it doesn't look like a one-dimensional curve, but it's an n-dimensional curve. And here the results, unfortunately, are not favorable, because you can show that as you grow the number of dimensions, the number of samples that you need to take in order to approximate a function to accuracy epsilon grows exponentially with the number of dimensions. So this is, again, it's not a single result, it's a class of phenomena that are called the curse of dimensionality. So it's a statistical or geometric phenomena that explain how functions behave in high dimensions, and the term itself actually goes back to Bellman, who spoke about the curse of dimensionality in physical problems. Now, in these problems, simply, if you think of images, right, of even something like 30 by 30 pixels, which is probably the smallest image you can imagine, digits from the MNIST data set, the number of dimensions will be approximately 1,000. So if you count the number of samples that you need to take, if you took this kind of straightforward approach, it will probably be more than the number of not only the cats or dogs on Earth, but probably close to the number of particles in the universe. So there are not sufficiently many animals around just to do it. And this kind of problem of cursive dimensionality, right, or you can also call it combinatorial explosion, was brought up in another report that is associated with the AI winter, which is the Lighthill report in the 70s. It was commissioned by the analogy of the DARPA, or basically the British funding agencies, and that was the point of time where they decided to stop funding these crazy ideas in looking at neural networks. So what happened, of course, was this AI winter, but at the same time, people continued working on these architectures, and some interesting ideas came from the field of neuroscience, from the study of the organization and the function of the visual cortex, the famous experiments in the 50s and the 60s done by Hubel and Wiesel, a duo from Harvard that won the Nobel Prize in medicine for understanding the organization of the visual cortex, where what they found is that the cells in the cortex were organized with some local shared weights, and this was reproduced by Fukushima in his famous neocognitron paper in 1980. So the idea here was a neural network that does, it has two types of neurons, so neurons that he called simple neurons, and neurons that he called complex neurons, so one in modern terminology that would correspond to local filters and pooling operations. And he worked on OCR type problems, so character recognition, and the problem, of course, if you treat these type of problems with the standard perceptrons, if I give you a digit of digit 3 and I move it just by 1 pixel, you see that the input into the neural network can change dramatically. And in fact, he complained that perceptrons were not by design invariant to these translations. So his architecture actually is remarkably modern by modern standards. So it was 7-layer network, so I think we can call it deep by modern standards. It had local connectivity, what neuroscientists called receptive fields. The filters were nonlinear, and he wrote in neuroscience terminology, so he talked about inhibition and activation. He had average pooling, so these are the complex layers. He used ReLU activation, so already in the late 60s, that was common. But the training was not done using backpropagation, so it was a kind of unsupervised type of clustering approach. And backpropagation, again, it existed already maybe in some other forms, but this is how neural networks were trained. So Rosenblatt had a special rule for a single layer perceptron. Then there were some other methods that were developed in the 60s, and then backprop became really popular in the 80s, starting from the paper of Rumelhart. So LeCun, who was a just a fresh graduate at that time, and he was working on actually the application of backpropagation in neural networks. Was interested in neocognitron, and he also happened to work at AT&T, which they were developing the first digital signal processors at that time. So basically, there was a good application to implement on a DSP, and basically he stripped down the kind of neuroscience terminology of Fukushima, replaced nonlinear filters by linear filters that could be implemented as convolutions. Actually, the first paper never mentioned the term convolution. The name came after, I think in '89, or even later. And he was able to show in real time complex pattern recognition tasks, such as recognition of handwritten digit, which was a difficult task at that time. It was actually deployed in commercial applications. They were working with banks and the post office, and that's where the MNIST data set comes from. But the computer vision community took a different path, and the late 90s and the early 2000s, probably until the first decade of this century, the approaches that you would typically use for image recognition were to detect some local features, then compute local feature descriptors, and then create some representation that would be passed into some very simple classifier like a support vector machine, which also were considered to be more favorable by mathematicians because you can prove, for example, global optimality results about them. So there are many papers written. So SIFT, the scale invariant feature transform, one of the most cited papers in computer science ever, was extremely well engineered feature detector and feature descriptor for these tasks. And what happened in 2012, as you probably all know, that all these carefully designed, handcrafted features were beaten down by a very large margin by a convolutional neural network. So it was this lucky confluence of the computational capabilities of hardware, the GPUs, as well as availability of large data, the ImageNet benchmark, which contained millions of annotated images, that finally allowed these architectures to shine. And since then, all the best results in this benchmark were by deep learning. So if you look at the AlexNet architecture that won this benchmark in 2012, it is more or less the same as what was done by Lekana. It's just slightly deeper. There are some different architectural choices. It has way more parameters. It was trained on GPUs, which, by the way, was not novel. GPUs were used for general purpose computing at least a decade before, and for training neural networks probably at least 7 years before. So in a sense, it was very careful engineering and application of existing ideas on a very large data set, and a very important problem that convinced everyone. Yeah, there is a question.
Sorry to go back a couple of slides, but you were mentioning Fukushima's implementation and no sort of backpropagation learning. So like, was he giving some kind of neuroscience, how do you say, proof for this? Or like some kind of Hebbian learning, or how did he?
I don't remember what kind of rule he used. I think it was inspired by some hypothetical ideas of how the brain learns. Yeah, but it was not backpropagation. Okay. He showed many other things. So he showed, for example, geometric stability, stability to noise. But again, it was in the early 80s. So the training examples were very rudimentary, so black and white letters.
Okay. Thank you.
Right, so basically all the rest is obviously history, right? So the people who started the deep learning thing got the Turing Award and now are all very famous. And basically this is technology that has really transformed the field, both the academical subjects and the industry. So just to give you, we'll be talking about graph neural networks, and you probably heard from Miguel as well in the previous lectures about graph neural networks. So just to give you a little bit of history of this one. So they're actually very much related and rooted in chemistry. And chemistry is probably one of the fields of science which is data intensive. It produces a huge amount of data, experimental data. And since early times, chemists try to organize this data, first publishing these humongous books containing information about molecules or chemical reactions. And then it appeared, the first digitized archive, the Chemical Abstract Service, and also with the appearance of the first computers came the need and the idea to search for molecules, right? So if, for example, you're a pharmaceutical or a chemical company and you want to patent a new molecule, how do you know that it has not already been described, right? So you need to search fast for molecular structures in some data set, and these were the first ideas of chemical ciphers that describe a molecule as a string and then try to match it in some data set. So that was the kind of problems that this guy, so he was a Romanian chemist called Vladuț, that was one of the pioneers of a field that later became known as chemoinformatics. He was trying to look at molecules as graphs. And as you probably know, the term graph itself, in the sense of graph theory, also is associated with chemistry. This is how Sylvester called the first attempts to design structural molecules structural formula of molecules. Basically trying to understand how atoms are related to each other with their chemical bonds, not only just the number of atoms and the types of atoms. And as you probably know, this was one of the first structural formula of benzene that was derived by Kekulé. And the legend says that he dreamt of a snake biting his own tail, so he came up with this kind of aromatic ring that is described here. So these kind of problems inspired these duo of mathematicians. We'll talk about them later, Weisfeld and Lehmann in the 60s, to devise an algorithm that would test whether two graphs are structurally similar, what is called the graph isomorphism test. And these ideas maybe were unnoticed, so there are many related works in the machine learning community and also in the chemical community trying to devise new types of neural networks that could take as input not vectors, not images, but graph-structured data. And the early works by Alessandro Sperduti in the 90s, for some reason, most of the works were by Italians, and probably the most cited ones are by Marco Gori, Scarselli, and others. And interestingly, about 10 years ago, graph neural networks returned triumphantly to chemistry, so I think worth crediting David Duvenot and Justin Gilmer for who also introduced the terminology of message passing neural networks that try to predict properties of molecules modeled as graphs and learning on these graphs. And then, of course, the ideas of geometric deep learning, as we'll see, maybe with some extra stuff. Also, the structural biologists have had their own ImageNet moment with AlphaFold, first in 2018 and then in 2020, basically predicting the structure of protein folds. So, and this field is very rapidly developing. So I think these are very exciting and cool problems that you can address with geometric techniques. So let's just try to summarize basically what this historical excursion gives us, a kind of blueprint for different architectures. So if you look at convolutional neural networks and graph neural networks, right, they work with very different data. Convolutional neural networks work on images, graph neural networks work on graphs, right, let's say molecules. But there are some common patterns, right? So in both cases, we have some underlying domain. So in the first case, it's a grid. In the second case, it's a graph. We also, in both cases, have some kind of geometric operation, so a symmetry, right, that is natural in the context of the problems that we are considering. So in images, it's translation, right? So I want to move, for example, an object in an image, and I don't care where the object is located if I want to classify it. In case of molecules, it's a permutation symmetry, so no matter how I order the atoms in a molecule, it's still the same molecule, right? So I want somehow to be insensitive to this ordering. And we can also define natural operations that respect this symmetry, right? So in case of convolutional neural networks, it's actually the convolution operation. I can move a patch around an image and apply the same weights or the same local rule that would extract the features. And as we'll see in graph neural networks, this is some kind of local rule that we call message passing, right, or some versions of it. So these are ideas that as you see, these are two examples of architectures that share the common principles, and that's the idea of geometric deep learning. So I can probably take the credit of inventing the term. So that was that happened when I was writing one of my ERC grants back in 2015 probably, and of course everybody was doing deep learning. So you need to distinguish yourself from everyone. So I wrote that we are not doing deep learning as everybody else. We are doing geometric deep learning. So that was the idea. Then we popularized it in this paper in IEEE Signal Processing Magazine, and more recently in a book that I'm writing with my collaborators. So by analogy to the Erlangen program, we can think of a kind of common denominator for machine learning architectures. So we would like to take this zoo of different architectures that were historically designed for different types of data with different kind of problem in mind, and look at them from the same perspective. And this perspective is through the lens of group theory and properties like invariance, equivariance, and symmetry, right? And if we've seen before this problem of machine learning in high dimension, right, where you have, for example, your images of cats and dogs as points in a high-dimensional space, we no longer consider these inputs as just a high-dimensional vector, right, that you need to put through some generic class of functions, and then you suffer from the curse of dimensionality. But now we know that there is some domain geometric structure that underlies these inputs. And in images, for example, this is a two-dimensional grid. So our data lives on some typically low-dimensional domain, and this domain comes equipped with some group, right? So in this case, it's the group of translations. And we have a domain, we have a group, we have signals that live on this domain, and the group that acts on the points on the domain. We see how it can act on the signals themselves through what is called the group representation, right? And in case of images, again, the group representation will be just the shift operator. We'll see it in more details. And then finally, we have functions that act on these inputs that somehow need to respect this symmetry. And this will be through what we will call invariance and equivariance, right? So we want the function either to be insensitive to how I transform the input by acting on it with the group, or should change in the same way, right? And I should say that the choice of the group and the domain are two separate things, and they're not only dependent on the data, they're also dependent on the task. So I might have a problem like this, right? So I have, for example, images of traffic signs, and if I'm designing a self-driving car, it's very unlikely that I will see rotated traffic signs, right? They will probably be aligned and move just horizontally and maybe vertically. So here, for example, the group of transformations that is reasonable to assume will be just two-dimensional translation, maybe even one-dimensional translation. But if, for example, my car can also tilt, right? So imagine that it's a plane and not a car, then rotations are also perfectly valid, right? So then the group of transformation will be different. So it's still the same domain, the same data, but the task might be different, and therefore the assumptions about this, the prior in this problem might be different. And if think of another application, if I have, for example, a pathological sample, so essentially a glass of some stained tissue that I put under a microscope. So there I can also have reflections, right? Because I don't have a canonical orientation for this glass. So it can be an even bigger group in this case. And again, task dependent. So as I mentioned, in case of images, the representation that we'll be working with is the shift operator. In case of graphs, actually the symmetry, as we've seen it, is the group of permutations, what is sometimes called confusingly the symmetric group. So it's the different ways that I can rearrange n different objects, and its representation is a permutation matrix. And as we'll see, the way that it's implemented, so functions that are equivariant with respect to this symmetry are message passing. And we can also have another type of architectures that are also confusingly called equivariant neural networks or equivariant transformers, where in addition to the symmetry group of the domain, we also have symmetry group of the data. And this is typical for geometric graphs like molecules, where the nodes also have geometric coordinates, so they live in three-dimensional space. And in addition to reordering the atoms in the molecule, we can also rotate or translate the molecule in three-dimensional space, right? So you want to be equivariant with respect to both transformations, so it's a kind of analogy of the external and internal symmetries you have in physics. And basically, geometric architecture is just sequences of equivariant or invariant layers. You can also interleave them with pooling. So I will not talk about it too much, but pooling is implementation of another principle that is important in physics, which is called scale separation. And this is what makes physics work. So if you consider, for example, let's say this room, right, and how we are surrounded by probably a quadrillion of different molecules that move very fast and collide with each other, but that's not how we can model the behavior of gas in some space, right? It's computationally intractable to trace all the molecules. So fortunately, there are just a few parameters that explain statistically how these gas behaves, right? Like temperature and pressure. And this is the main principle of statistical mechanics. But if we want, for example, to model how Earth with its very complicated atmosphere moves around the sun, again, we can completely disregard it and consider it as just as a point, because at that scale, all these details are completely irrelevant. So the scales, of course, interact with each other. So this is maybe a wishful thinking. And in neural networks, you can also mathematically show that in some architectures, pooling operations are necessary for them to operate correctly. So these ideas can be applied to different types of objects, to geometric domains, traditionally to grids, but then also to graphs, maybe to general homogeneous spaces, and then also maybe to more exotic things like manifolds, meshes, and geometric graphs. And if you look at some of the standard architectures that are very commonly used in deep learning, whether it's CNNs or maybe LSTMs or deep sets or transformers or GNNs or intrinsic mesh convolutional networks, they can all be derived from the same blueprint. So there is some kind of domain and associated symmetry and associated invariance that you can bake into your architecture, and you get basically as particular instances of this blueprint some of the most common and famous architectures. Any questions so far before we start talking in detail about graphs? So if I have time, I will try to cover all these different domains, but I will probably spend most time on graphs and also some physics-inspired perspective on these architectures. Yep.
Yes, I will have a question. So if you coin the term geometric deep learning, is there an alternative, like non-geometric deep learning or like traditional deep learning, or what does it mean, or yeah?
Well, so it's a very broad term. So I think we use it maybe in a very broad sense. So it's using geometric ideas or geometric techniques to interpret and build deep learning architectures, and vice versa, applying deep learning to geometric objects. Now, whether, for example, the model of group invariance and equivariance is really the kind of ultimate truth, of course not. So it's a mathematical abstraction, and in most cases, the transformations, for example, you have in images, they're actually not well described by groups, but at least it's a good starting point. In many cases, for example, in molecules, this is kind of physical reality, so an inductive bias that you rather want to incorporate in your architecture.
Okay, I have one more question. Could you please take back to the previous slide?
Yeah.
Because you mentioned like the existing neural networks architectures and the group of symmetries. And do you think there is any other group of symmetries that we in real world applications should think about, and because of that create some new architectures that is, I don't know, for example, well suited for them?
Yeah, so it's a good question. So there are some other architectures, for example, mostly coming from physics. So of course in physics you have interesting groups. So I think there are some Lorentz invariant, for example, neural network architectures. You can also combine some groups. So I will show some examples. So you can have, for example, products of permutations or some special group products of permutations in subgraph neural networks. So it's a general blueprint. So if you can follow the blueprint and design an architecture that implements this invariance that is relevant for your problem, then you have a way of doing it.
Okay, cool, thanks.
Yeah, there are also some works that try to discover the symmetry group from the data and from the problem. So that's also an interesting direction.
Could you shortly address the symmetries which the transformers go for? Because I still have difficulty to think in this symmetry perspective.
So I will talk, well, it will take me probably about 20 minutes, but we'll get to transformers, yeah. So transformers are special types of graph neural networks. You can think of them this way.
So on the slide, there's the LSTM, and so it's written that time warping is, you could have architectures that are invariant to time warping, but if you look at speech recognition, so maybe first of all,
we humans also don't have that, right? So if something is super slowed down, we're probably not going to notice what it is. So my question is there any other invariants or equivariants for time series data that you can think of?
So, well, here, what I mean by time warping, you can actually show that gating is a necessary mechanism to be able to accommodate time warping. So basically, gating emerges as basically as the architecture for these kind of invariants.
Okay, got it. Thanks.
Yeah, I think there is a question there.
So okay, so you said that you will talk about transformers more in in the next few slides, but I wanted to ask about one of their emergent properties, like in relation, for example, to CNNs, namely that CNNs have kind of encoded in them by definition translation invariance, whereas transformers don't. And I think it has been discovered that transformers actually kind of learned the translation invariance from thanks to the amount of the data that they consume, but they weren't defined to do that. It's this translation invariance just emerged from the data. So I was wondering whether, in your opinion, it is better to use more generic architectures which learn those inductive biases from the data, or whether we should encode the inductive biases in their architecture, and face the risk that a specific inductive bias may be also a limitation.
Yeah, well, I think the answer is already contained, at least one of the answers in your question, right? So the amount of data is obviously a limitation, so it might be easy to collect data like images, right, or maybe text. It might be much more difficult to collect data that comes from, I don't know, biological experiments, right? So if the data is limited and the data is expensive, then probably you want to work hard to incorporate as many inductive biases as you can. In some other applications, actually the inductive biases or some symmetries or some invariances come from the problem that you're trying to model. I think it's true for many applications in what is called AI for science, right? So if you have some, I don't know, physical system, you know that certain properties will be conserved. So it makes no sense just to use a generic black box that will be producing unrealistic outputs, right, that are physically incorrect. But there is no, so it might be that in problems where you don't know a priori what symmetry or invariance you have, it might be a good idea to use transformers if the computational complexity and the scale of the data allows it.
Hello, I have a question about augmentation. It feels like, at least at image case, augmentation is basically exploiting this group symmetry, right? Like you augment by do some translation, but if you use some geometric-based architecture, maybe then you don't need to do augmentation anymore. So what's your opinion of augmentation? Is it like an artifact or something?
Well, so augmentation is a technique of basically of when you have a limited amount of data, you can generate synthetic data that looks like what the kind of data that you want to see in your application. This was actually one of the important features of the AlexNet, for example. So they use certain type of data augmentation for images to make it more robust. So again, you can incorporate this kind of inductive biases into the architecture. Sometimes it might be difficult. So another aspect that is often overlooked is actually the hardware, right? So it's very easy, and it's probably more a coincidence, at least originally. The convolutional neural networks map very nicely to the type of hardware that is used in the GPU, the single instruction multiple data type of architecture. So it was not by design, because the GPUs were designed for different types of problems. With other architectures, it might not be the case, right? So with graph neural networks, for example, this is not the case. So there might be some better, so to say, architectures, maybe from mathematical standpoint, but they're just not as convenient to implement. And therefore, maybe you will prefer to use something that is less correct, but you can do data augmentation, and the hardware allows you to implement this architecture better. Yeah.
What do you think, this is a follow-up question about augmentation, what do you think about augmentation not as a simple tool for increasing the size of the data set, but as something, as in contrastive learning, as enforcing the symmetry? Can it be kind of equivalent to the symmetry you define? Well, it was used in this formula. I mean, like, can the load of enforcing the symmetry be shifted towards augmentation, not to the model?
Yeah, so basically you're sampling points from the group orbit, right? So that you can think of it this way as well. Whether it's enforced in a hard way or in a soft way, that's probably not that important. Yeah, so data augmentation is a very valid technique if you know exactly how to do it. And yeah. Okay, so let's move on to graphs. And graphs, as you probably know, the idea itself is pretty old. So it's usually attributed to Euler, who was thinking of these kind of problems, right? How you can connect land masses without actually accounting for the particular geometry, but only how what is nearby, right? So the famous problem about the bridges of Königsberg, and this is what he called the geometria situs, or basically the geometry of place. What in modern terminology we call topology. So the term was actually introduced by Poincaré, who by analogy to Euler's terminology called it analysis situs, and that was also where his famous conjecture appeared. So we will talk about Poincaré conjecture actually later. I hope to get there as well. So graphs, obviously I don't need to convince you that graphs are interesting and important. So more or less anything from very small scales or very large scales can be modeled as a graph. So any system of relations or interactions, whether it's a molecule, where you model how different atoms interact with each other through chemical bonds, to, for example, interactomes, right, in biological science, how different entities in our body or in a cell interact with each other, different, for example, chemical reactions, or even social networks, right, describing relations, friendship, interactions between different people. So this is modeled as a graph, and again, graphs can be of different types. So let's consider a simple model here. So we'll consider an undirected graph. So it means that we have a collection of nodes, and we have unordered pairs of nodes as edges, right? So just pairs. Basically, the order doesn't matter, and the nodes are described by d-dimensional vectors. So these are features that are attached to the nodes. And of course, it can be more complicated. So you can have graphs that are directed. You can have both continuous and categorical features, both in the nodes and the edges. But just that would be already interesting enough to look at this kind of object. So one thing that characterizes graphs, right? Basically, this is again a topological construction. So it's an abstract object that lives on its own. The moment we need to represent it on a computer, we describe it, for example, as a matrix, right? So we can describe the structure of the graph as the adjacency matrix, right, of size n by n. N is the number of nodes, so we have one if there is an edge between a pair of nodes, and 0 if there is no edge, right? And if the graph is undirected, then this matrix is symmetric. And the features, we can describe them as a matrix of size n by d, right? D is the dimensionality of the node features. So one key thing here, which is already written on this slide, is that we don't really have a canonical way of ordering the nodes of the graph. So when I make this description, I automatically assume some ordering of the nodes, but this ordering can be like this or can be like this. So anything that will take this description of the graph as an input must account for this built-in ambiguity, right? So I somehow need to be able to produce outputs that disregard in a correct way all these possible permutations, right? And the two types of problems that we can consider in relation to graphs, there are actually more problems, but let's say these are the prototypical problems. One is graph level problem. So I give you an input graph and I try to output a number that describes this graph, right? Or maybe a vector. Like, for example, I'm predicting the chemical properties of this molecule, like water solubility. So the input is a graph describing a molecule. The output will be some number, right? Another class of problems, I give you a graph and I want to do node level decisions, right? For example, I want in a social network to classify which of the users is behaving badly, right? Maybe a spammer. So in the first case, I give you a graph, right? And the output, no matter how I permute the inputs, should be the same, right? So we're talking about a permutation invariant function. So mathematically, it can be described like this. So, right, so the function here now is a function of x, the node features, but also the structure of the graph. So they both form the input. And here I act on these two inputs with a permutation matrix, which is the representation of the permutation group. You see that actually the representation is different for different types of objects. So the features, you can think of them as vectors, right? So I permute only the order of the rows. The adjacency matrix, it's a two-dimensional tensor, so I act both on rows and columns, right? I need to permute both rows and columns here. Is it clear? And together, these form a permutation invariant function. In the second case, if I want node-level predictions, the output has the same structure as the input, right? So if I change the order of the inputs, the order of the outputs is expected to change in the same way, right? And here I'm interested in permutation equivariant functions. So equivariance means changing in the same way. So the output now will be, well, some kind of vector, right, or a matrix, denoted by F capital. And if I permute the input, the output will be permuted in the same way, okay? Now, what are graph neural networks? Essentially, these are parametric graph functions. So I provide you a graph as an input, right, or these matrices X and A, and I output something, right? And something here, as we'll see in a few minutes, is parameterized by some vector of parameters. And sometimes there is no distinction made between graph neural networks or message passing neural networks, so we want to make this distinction, but sometimes they are used synonymously, right? So most of the graph neural networks that are used in practice are of the message passing type. We'll see exactly what it means in a second. And graph neural networks, again, you can consider them as a special instance of these geometric deep learning blueprints. So we have usually a sequence of permutation equivariant layers that produce node-wise predictions, and permutation equivariant in the sense that if I change the order here, it will change in the same way here. And then if I have graph level tasks, I will have permutation invariant pooling, right? That aggregates all the information from these node features and produces a single output for the graph. And the typical way that they work is by neighborhood aggregation. So you can pick up a node in the graph, right? Let's call it I. And now I look at the neighborhood of the node. By neighborhood, I mean all the nodes that are connected to I by an edge, right? So this is how the neighborhood of I looks like. And I can look at the feature vectors associated with these nodes, and you can see that even though the neighbors are unique, right, the feature vectors are not unique. So this is encoded by color, so these two nodes have exactly the same feature vector, right, just for this example. So together they form what is called a multiset, right? So it's a set where the same object can appear more than once. And we also have the feature vector of the node itself. So I want a function to aggregate them locally, right? Let's call this function phi. And again, the characteristic property of this function is that I don't have a canonical ordering of my neighborhood, so the feature vectors can appear like this to this phi. So it must be by design permutation invariant, right? It cannot assume any order in which the neighbors come. We can make it more complicated and we can incorporate additional information, but again, as a basic structure of a graph, you don't have this order, right? Now you can repeat this process everywhere, at every point, at every node of the graph, and this is actually very highly parallelizable, at least in principle. And once you do it, you get an output, right? That for every node of the graph, you output some vector. And this is also a function of the graph, and you can easily see that if my choice of this local aggregation is invariant, then the output is equivariant, right? So if I change the order of the x's here, then the output will change in the same way. And most of the graph neural network architectures differ in the choice of these phi, in how I aggregate locally the features. And while there are probably zillions of different architectures, most of them fall within the following three categories. So the first one is what is called convolutional graph neural networks. And you can simply think of convolutional neural networks as just summing up the features of the neighbor nodes. So this is what I write here. So the update for the representation for the feature at node I is the sum of some transformed neighbor nodes, right? Psi will be some learnable function. Xj is the the feature of the neighbor node. Here it is. And A, I, J are coefficients that depend only on the structure of the graph. In this simple case, just the elements of the adjacency matrix, right? And here, sigma is just some nonlinear activation, typically Relo, right? So that's how a convolutional type graph neural network looks like. Yeah. Yeah.
Is this convolution here equivalent to 1D convolution, something like that?
So we'll see it. We'll see it well, not in a second, but we'll see it later. Yeah.
Okay.
So basically, you can obtain convolution when the graph is a grid, and we can actually see that convolution on a grid is a special type. Basically, it's a unique linear equivariant function. So basically, yeah. So that's why the term convolution is appropriate. So it's an extension of convolution to graphs, right? And you can write it in this form, right? So if I write it as matrix multiplication, so X is my feature matrix of size n by d. I multiply it from the left by some matrix A, right? The diffusion matrix can be the adjacency of the graph. It can be something else, but basically it propagates information between adjacent nodes. And on the right, I have, in the case of a linear transformation of the nodes, it's a learnable shared matrix that acts on every node in the same way, right? On the features of every node in the same way. We'll see that it's related to diffusion equations on graphs. And this is probably the simplest version of a GNN. It's highly scalable. You can basically, it's just large matrix multiplication. It has been used in industrial use cases. I think the first to use these kind of architectures was Pinterest with PinSage. We also used it at Twitter. And then there are some statements about these architectures in the kind of graph neural network folklore, saying that it works only on homophilic graphs. So by homophily, I mean this assumption that my neighbors are similar to me. Typically, the assumption is that the labels in the neighborhood are somehow similarly distributed to the label of the node itself. And here's an example of a homophilic graph versus a heterophilic graph. So, and the usual motivation that is given that this matrix A typically will look like a low-pass filter, right? So you're somehow averaging your neighbors, and if the neighbors are of the same type, then it will work, and if the neighbors are very different types, then it makes more harm than help. And this is actually not true. So I hope to convince you that the story is much more nuanced. There is also this channel mixing matrix, and there is an interesting and subtle interplay between these two matrices, and we'll be able to see how it works from the when we consider graph neural networks as differential equations. So slightly more interesting architecture is an attentional GNN. So here again we can think of it, at least in some settings, as a linear combination of the features of the neighbors, maybe transformed by some learnable function. But now the coefficients depend not only on the structure of the graph, but also on the features themselves, typically through an attention mechanism. So the most famous representative of this architecture is the GATT, the graph attention network. And in the most general case, right, so we can write GATT like this. So that's if we have a linear combination, a sum, so we have linear combination with the matrix, but now the matrix is actually a matrix valued function of X, right? So it itself depends non-linearly on X. And the most general case is message passing architectures, where we have a bivariate function that depends on the feature of the node and the neighbor, and this is the other cases are specific cases of this architecture. And it was shown that message passing GNNs with specially chosen aggregation function, in particular it has to be injective, in certain restricted settings, again, allow me not to go into the details, are equivalent to graph isomorphism testing algorithm that was derived by Weisfeld and Lemon that I mentioned in the beginning. And let's talk about this. So basically, from theoretical standpoint, what actually graph neural networks do, right? Or message passing type graph neural networks do. So first of all, what is graph isomorphism problem? It's telling when two graphs are the same, right? So I'm writing here equal, but of course it's not equal, so it's equivalent in some sense. And what do I mean by this equivalence? What I want to say is that there exists an edge-preserving bijection between the nodes of these graphs, right? So in other words, I can find a correspondence between nodes in G and G prime such that if there is an edge between a pair of nodes in G, then there is a corresponding edge in G prime, right? So is this bijection unique? What do you think? No. When is it not unique? Exactly, when the graph has symmetries, right? So this is an example. Actually, this graph is a good example, right? So you can reflect the nodes on the left and the right, and then you can have another bijection, right, like this. So this bijection is not unique. But for determining if two graphs are isomorphic, it's sufficient to say that there exists such a bijection, right? So that's what tell us that the two graphs are equivalent, right? So basically they are the same up to the ordering of their nodes, right? So if I look at their adjacency matrix, they will be the same up to applying some permutation, right? So I can relate the two adjacencies by permutation. And related to the question of universal approximation, right, which is fundamental for traditional neural networks like perceptrons, we can show that a class of functions is universally approximating permutation invariant functions on graphs with, importantly here, the limitation finite node features, if and only if it can discriminate graph isomorphisms, right? So basically, universal approximation is equivalent to graph isomorphism testing, right? So basically, the two things go hand in hand. And if you ask what kind of graphs can we represent with message passing neural networks, right? So here is, let's say, the space of all graphs. And these would be graphs that are structurally equivalent, right? That is isomorphic. So by construction, we know that graph neural network, it cannot distinguish between these graphs, right? They're exactly the same up to ordering of the nodes. So just by construction, it will produce the same output for any isomorphic graphs. But the question of the opposite direction is more interesting, and this is not necessarily guaranteed, right? So I might have different graphs that are not isomorphic, like the reds and the blues, that by chance will have the same representation. So the graph neural network will output the same output for these different graphs. So in other words, if we have the space of all permutation invariant functions, right, and we know that these are all graph isomorphism discriminating functions, this is where we'll sit a subclass of functions that can be computed by message passing. Okay, and so the question of graph isomorphism, as I mentioned already, it came from applications in organic chemistry where people try to compare structures and try to determine whether two molecules are the same, right? So the case of isomorphism is a special setting, right? You can also think of distances between graphs. And Weisfeld and Lehmann in '68 came up with an algorithm that they believe to be a polynomial time method for determining whether two graphs are isomorphic. So I should say that at that time in the '60s, even the notion of complexity was not totally spelled out. And also the understanding of what's the complexity of graph isomorphism testing as a computer science problem was not understood. Actually, it's not understood even now. So we know that it's not NP hard, and we also don't know polynomial time algorithms for it. So it's a special complexity class that is called GI class. But anyway, so it was actually disproved by a counterexample. So it was an example was shown that of a class of graphs that cannot be tested by the Weisfeld-Lehmann algorithm. We'll see such examples in a second. But the way that it goes, it's essentially a color refinement procedure. So it considers a graph without any features, considers only its structure. And initially, the graph has every node labeled in the same way. By label, I just mean a natural number that is attached to a node, right? And what the algorithm does, it takes a node and looks at its neighborhood, right? And you can see that originally in this graph, we have two types of neighborhoods. So we have a blue node with two blue neighbors, like this. Sorry, that's blue node with three blue neighbors and blue node with two blue neighbors, right? So these are two neighborhoods that we see in this graph. So if I now apply an injective function that I call phi, right? Think of it as hashing. I will have two distinct outputs, right? So I will have nodes of the yellow type, let's call it, and of green type, right? So I will be able to distinguish between these different neighborhoods. So now I have a graph with refined labels. I can apply the same procedure again, and now we have three types of neighborhoods, right? We have green with one green and one yellow neighbor. We have green with two yellow neighbors, and we have yellow with two green and one yellow neighbor, right? And these become, again, distinct colors. So this will be, let's call it violet, gray, and orange. But if I repeat this procedure again, the colors will stop changing, at which point the algorithm stops and produces a histogram of colors, right? So that's a graph level descriptor. You can think of it this way. And what they show in the paper, well, the paper is actually complicated to read, but that's, let's say, a reduction of it. It actually describes a different type of algorithm, what is called 2WL, that does edge color refinement, but it doesn't matter. It's equivalent to what I'm showing here. So if I give you another graph and the distribution of colors is different, then I can guarantee that they are not isomorphic. But if the distribution of colors is the same, like in this case, we actually don't know. So it's a necessary but insufficient condition. And in fact, you can find examples of non-isomorphic graphs that would be deemed equivalent by WL test, right? Or in this case, WL test cannot determine whether they're not isomorphic. And you can also see why, the reason for it, right? Basically, what it does, it refines the colors of the node, so every node looks at its neighborhood. And this is how the neighborhoods of nodes look like, right? So this node has 2 neighbors, then this node has again 2 neighbors, and so on and so forth, right? So if you look at the structure of these neighbors, they will be exactly the same in both cases, right? And actually, very simple examples of graphs, for example, regular graphs where the degree of every node is the same, cannot be tested by this simple procedure of Weisfeld and Lemon. You can also not count connected patterns of more than 3 nodes, like triangles or cycles. And this is, I think, astonishingly disappointing, given that the algorithm came from applications in chemistry. So in chemistry, these would be 2 different molecules, right? And this has a 6 ring, and this has a 5 ring, right? So or 5 cycle, using graph theory terminology. So we cannot distinguish these molecules by the Weisfeld-Lemon test. They would appear potentially the same, right? So we wouldn't know. So basically, the functions that can be computed by WL are strictly smaller than all permutation invariant functions, right? And we know examples of functions that cannot be computed by WL. For example, we cannot count the number of rings, right? So if I want to implement a function that counts the number of rings in a graph, I cannot do it by means of WL tests or by means of message passing. Now, the relation between WL and message passing is not random, right? You can see even the structure of the algorithm is exactly the same, right? So this is what WL test does, right? So it updates the color of every node by looking at the structure of the node and the multiset of neighbors, right? Here X denotes the colors. And this is what MPNN does, right? So here the square denotes some general permutation invariant aggregator. Can be sum, can be max, can be min, can be anything, right? Importantly, it's permutation invariant. So we can see that it's a special case. So MPNN expressive power is upper bounded by the Weisfeld-Lemon test. And the question is when MPNN is as expressive as WL test, right? So basically, we're interested in this case, right, when the 2 circles coincide. And if you look at different types of aggregators, right, so imagine that this is your input graph. So I have this gray node that has 2 types of neighbors. We have green neighbors and we have blue neighbors, right? So if I consider the input as a multiset, right, I completely disregard the structure of the graph itself, right? So what the node sees is just a soup of the neighbor features. So if I use a maximum aggregator, I cannot distinguish between this and this, right? Because for the maximum, it doesn't matter how many times each of these features appears, right? If I use a min, then I cannot distinguish between this and this, right? I can multiply the neighbors by some constant factor. The sum, though, allows to distinguish between all of them, right? So you can think that maximum gives you a kind of skeleton of the set, and the mean gives you the distribution, but the sum is strictly more expressive, right? And here's an example of structures that max or max and min would fail to distinguish, and indeed sum appears the most expressive one. And if you assume that, so the theorem about the equivalence between WL and message passing states that if you assume that the node features come from a countable universe, then if you have an MPNN with injective aggregator, call it square, an update function phi, and graph-wise readout function is as powerful as the Weisfeld-Lemon set, right? And the assumption here is of discrete countable features, which is not always the case in practice. And then there is an architecture that actually implements that is equivalent theoretically to the Weisfeld lemma, which is the graph isomorphism network, or GENN. So basically it uses a sum aggregation. So the epsilon here is just theoretical thing, so there exists infinitely many constants epsilon that you can use here. So we know that basically there exists at least a choice, right, within the all possible message passing neural networks that makes it as expressive as WL, but of course we are interested in more expressive architectures, right? Can you do better than WL? And here again there is an entire universe of different architectures. So some of them actually go beyond message passing, at least in the traditional sense. And roughly you can distinguish between 4 different categories of approaches. So it's either higher order WL test. It's not a single test, it's a hierarchy of tests. The use of positional and structural encoding, so that's how transformers work. Subgraph GNNs, and then topological message passing, right? So let's talk briefly about all of them, and then when do we need to do the break? Sorry? So let's maybe 20 minutes, and then we do the break. So the first class of higher order WL tests, as I mentioned, so WL test is just one algorithm that was initially developed and then extended by Babai and collaborators, actually independently also by other people. So one of them was Eric Lander, who is mostly known as computational biologist, but he started as a mathematician. Basically this is an increasingly more expressive hierarchy of tests. Instead of doing node refinement, they look at tuples of nodes, so it's obviously computationally more expensive. And there is always, you can find a family of graphs that these algorithms cannot distinguish. So like strongly regular graphs for 2WL or 3WL tests, and what is called CFI graphs for general KWL. I should also say that this terminology of KWL is confusing because there are what is called folklore WL tests versus the classical WL tests that are slightly different. So, but overall the hierarchy, right, up to notation is the same. So we know that message passing GNNs are equivalent to the standard WL. You can also design just replicating in a neural network architecture the KWL test higher order K GNN. So this is what Hagai Maron did in his works. And then you can also have some other algorithms we'll talk about in a second that sit somewhere between. They don't exactly follow the hierarchy of the WL tests. So the second approach is positional encoding. And again, I remind you of this example of 2 graphs that cannot be distinguished by the WL test. But imagine that I could now attach some features to the nodes of the graph, right? And this could be even something as simple as random features. You see that now, because I have some extra information, I can distinguish between these cases, right? So if I look at the leaves, for example, of this tree, right? I can ask, for example, whether the root appears among the leaves or not, right? And here it does appear, and here it doesn't, right? So they are clearly different, right? I would be able to distinguish between them, right? So the coloring of the nodes removes, at least to some extent, the ambiguity. Now, of course, if I use random features, then the question is how can I reproduce them on a different graph? So these type of approaches are equivariant only in expectation. But there are other methods that can do better, and these are structural encoding. So the idea of structural encoding, you have some substructures, right? So you have a bank of substructures, let's call it H, and you can count the substructures, the occurrence of substructure for every node or for every edge, right? And there are 2 ways that you can consider subgraphs, whether what is called a subgraph or an induced subgraph, doesn't really matter, right? So there are 2 ways that are slightly distinct. And for example, in these 2 graphs, if this is my bank of substructures, let's say cycles of size 6 and 5, so in this molecule, at every edge or at every node, I will count once the 6 cycle substructure, and these nodes I will count it twice, right? Because this node participates in both structure on the left and the right. But the 5 cycle substructure doesn't appear here versus it appears here, right? So with this encoding, now I have some these additional features that I can attach to every node or to every edge of the graph, and I can use them in standard message passing, and this would allow me to discriminate between these graphs. And the complexity of this method is basically it's all hidden in pre-computation, so this counting of substructures. So in the worst case, it's order of n to the power k. K is the size of the substructure, so it could be large. But in practice, for structures, more friendly structures like triangles, there exist more efficient algorithms. So in practice, it can be way better. The algorithm itself, and especially the training part, which is typically more expensive, is standard MPNN. So it has linear complexity in the number of edges, or roughly order of n if the graph is sparse. And the theoretical result is that this kind of architecture that we call GSN, Graph Subtraction Network, is strictly more expressive than WL on certain assumptions on these substructures, right? So it should not be a star graph, or it should be a structure of size bigger than 3. And basically, you can formulate this that GSN is not less expressive than 3WL. You can also do it for different KWLs. Basically, you do it by counterexamples. So you can design a substructure that the standard WL tests cannot count, whether it will be clicks of certain type or other things, right? And the proof by example is something like this. So this is a strongly irregular graph. It cannot be distinguished by 3WL, but this graph contains 4 clicks, and this doesn't, right? So if I count 4 clicks, I would be able to distinguish between these graphs, right? So in a sense, it's a kind of cheating, right? So I'm not following really the KWL hierarchy, right? So this is an example of different structures I can count, triangles and clicks, but then basically the expressive power looks like this. So this is, for example, a graph subtraction network with 4-click count. So it might actually, there might be examples of graphs that are distinguishable by 3WL, but not by this method. But we have at least an example of a family that 3WL cannot detect, so it's outside of the hierarchy. And why this is important, especially in applications related to chemistry, because often we know these substructures a priori, right? In organic molecules, for example, cycles are a very prominent feature. These are what is called aromatic rings, right? Like in the molecule of caffeine, we have 2, right? So we have this ring of cycle of size 6 and cycle of size 5. And we see that if we incorporate this information as a kind of problem-specific inductive bias into the problem, we are able to much better predict the properties of molecules. In this case, it's I think the water solubility on a toy data set of molecules that is called zinc. And by incorporating cycles, we significantly reduce the error. Third class of approaches, what is called subgraph GNNs. And here the idea is also very simple. So if you look at these 2 graphs, again, this is probably one of the simplest examples of non-isomorphic graphs that cannot be tested by WL, right? If you do the color refinement, this is what WL produces, so the histograms are the same, right? That's exactly the case where you cannot say anything about the graphs. But imagine that I can perturb the graph, for example, by removing this edge, right? So if I did it, the colors will be very different, right? So this will be the distributions of the colors, and they are clearly distinct. So in this case, the perturbation allows to distinguish between structures that are otherwise indistinguishable. So the question is, of course, do I know which edge to remove, right? So here maybe I was lucky. And the answer is usually I don't. So let's remove all possible edges, right? So let's just make this perturbation when I remove 1 edge at a time, right? So, and there are 7 possibilities. I can also do node deletions in the same way, right? And now, instead of a graph, I have a collection of subgraphs that are extracted by some policy. So in this case, it's a very simple policy, 1 node removal, right? And actually results in graph theory that say that if I give you this collection, so in terminology of graph theory, this is called a reconstruction. So if they have the same multi-set of node remove subgraphs, right? So this is what we denote H tilde G, right? So graphs where basically if we look at these kind of multi-sets, they will be the same, of course, up to reordering. So the statement in graph theory that is called reconstruction conjecture claims that under some technical assumptions, if H is a reconstruction of G, then H is equivalent to G, isomorphic to G, right? So why it is called a conjecture? Because it is proved only for small graphs, and it's an open question in general. And there are generalizations for subgraphs where you remove multiple nodes. So this is, again, not a single result, so it's a class of results. It was introduced by Paul Kelly in his PhD thesis that was done under the supervision of Stanisław Ulam, who was a mathematician, a Polish mathematician, but he's probably more famous for initiating the Manhattan Project and developing thermonuclear weapons. So, but he also was he's also famous for many interesting results in mathematics, and this is one of them, the reconstruction conjectures. So we don't know whether this is true. So it might be true, but that's why it is a conjecture. It would be cool if it were true, because of course, in this case, I could test graph isomorphism by just doing something with this collection. So what exactly can we do with this collection, regardless whether the conjecture is true, right? So it will just give us stronger theoretical property of these architectures. So what we can do is we can consider our graph as a collection of subgraphs that are extracted from the given graph, right? And what is important to understand is that there is a correspondence between them, right? Because we created these subgraphs, right? So it's built on the same nodes. We just might remove some edges, right, or some nodes. So we have here two types of symmetries. So we have the permutation of the nodes in the graph itself, right? And we also have a permutation of the subgraphs in this multiset, right? Because we don't have a canonical order of them. So together, basically, the structure, the symmetry structure of this new object of this collection of subgraphs is a product of two groups, right? If we don't know the correspondence, there will be a special type of product that allow me to skip the details. And basically what we can do, we can design an architecture that does message passing on each of these subgraphs separately, but then fuses the information across graphs using this known correspondence. And this is probably more powerful than WL. A version of this architecture that we call subgraph union network, we can actually show that it's upper bounded by 3WL, and we hope that it will be equivalent to 3WL, but a few weeks after we published our paper, it was shown by a counterexample that it is strictly less powerful than 3WL. So we don't know exactly. It's surely more powerful than 2WL, but upper bounded by 3WL and strictly less powerful. So we have even a blog post about these different architectures, and there are multiple methods that are related. So one of them is, for example, you can do dropout on your neighbors. That was done by a work from the group of Roger Wattenhofer at ETH, and they actually showed that this has similar effect. So it increases the expressive power, not only gives some kind of robustness to the architecture. So the last more expressive type of message passing neural networks I would like to mention is what we can generally call topological message passing. And if you think of what is a graph, essentially it's a set where you glue pairs of nodes together, right? So every element in a set, right, or every node in a graph is a zero-dimensional topological object, right? So you can define this one-dimensional object, the edges that you glue to the nodes, right, and you get a graph. But you don't need to stop here. You can also define cells of higher dimension, right, that you, for example, glue to cycles in your graph, right? And we get what is called a cellular or CW complex, right? And basically now, instead of traditional message passing in graph neural networks where we exchange information between nodes along the edges, we can also go up and down in this hierarchy. So we can do message passing within the same dimension, right, of the cellular complex, but we can also go across dimensions. And this hierarchical message passing is strictly more powerful than the Weiss-Ferrell-Lehmann, and it's obviously very convenient for molecules, because in molecules these structures have some chemical meaning, and this probably is closer to how chemists think of molecule, because of course the graph captures all the information, but it doesn't make certain structures explicit. And in graph neural networks, for example, well, first of all, you cannot even detect by message passing the presence of these structures. And if you want to transfer information from this node to this node, you will need to do a few steps of message passing. Here we can do it at once. So it also gives computational advantages. And again, if you want some more details about how these different methods are related to each other, so there are many more expressive architectures. So there is a tutorial that was given at the LOG conference and recorded on YouTube by my PhD student, Fabrizio Frasca, with Beatrice Bevilacqua and Hagai Maron. So it's actually a very nice tutorial, and they go into much more details about all these and other different methods for expressive graph neural networks. Any questions so far?
I have a question about summation aggregation being the maximally expressive aggregation. Also, probably it is related. Maybe if you can also comment on the, what was it, discrete countable restriction on the features. Because if I imagine that our features are integers, there are different combinations of integers that sum up to the same number. So summing them actually does lose the information. And then, if that makes sense.
So countable doesn't necessarily mean integers, right? But they should not be continuous. So why this is, without going into too much details, basically they use the same proof technique that that was used in deep nets to prove the universality there. So this assumption is important. If you remove this assumption, then this proof doesn't work. So basically, they apply locally, kind of the result of deep net that works on sets.
All right, thanks.
Hello. Very interesting, thank you. I'm wondering about chemistry, whether you can encode in the features of your graphs also geometric information. Especially in chemistry, aromaticity is very important. Whether it's possible to encode it directly or you need some additional layers of information.
So some information you can probably compute, and of course if you can pre-compute it, if you know that these are meaningful features, then I think it makes sense to encode them. So the geometric information, I'm not sure that you mean information that comes from the positions of the atoms, right? Yeah, so I will talk about it in a second. So you can, basically when you deal with geometric information, you also need to do it in a proper way. So you need to do it in a way that is equivariant to possible transformations. But I think short answer is yes.
In case of these like increasing hierarchy of the KWL tests, is it a case that for a given KWL that we know there exists some message passing graph neural network that exists that can do it, but we just can't construct them? Or can we say that if we could make such a message passing GNN for such KWL, it would be, intractably huge and we would need to approximate it or something like that?
So first of all, it is intractably huge, so its complexity is n to the power k. So I think what is limited in practice is 3WL. So this is what Maron describes in his paper. I don't know, depending whether you can call it message passing or not, it depends on what you consider message passing, right? So because here you have more than pairs of nodes, I would argue that strictly speaking it's not message passing, but for example, Petr Velišković would say that it's message passing on a different graph, right? So it depends on the perspective.
Maybe one more follow-up question for this KWL stuff. If you have a particular application that you're interested about, are there some cases where you can say, for this class of problems that we're working on, it's enough to be able to distinguish up to such a level? Because the higher you go for K, obviously, like these edge cases would get really nasty, which you might not see in your application.
Well, so it's a good question, right? So, for example, planar graphs have a WL dimension of 3. So, basically, all planar graphs can be distinguished by 3WL test. And you can argue that molecules, right? Most of the molecules you can draw as two-dimensional structures. Maybe some of them you don't, but they're probably a tiny fraction. So, do you need something more powerful than that? The expressive power itself is probably not the end of the story, right? Because nothing tells you about generalization. Yeah, I don't think that this on its own is really the crucial consideration. It's good, of course, to have an architecture that is that allows to distinguish between broader class of graphs. But if it comes at the expense of computational complexity, for example, maybe it's a bad idea. So you probably want some kind of good trade-off between these. Thank you.
I had a follow-up question. So could you please define what message passing is in this case? Like, so can we give a short definition?
Right, so message passing is, what I call message passing is these kind of architectures. Let's see, where I had it. Yeah, so basically architecture of this kind. So this is the most general type of message passing. So we have the update of node I from neighbor j is done in this way. So I have a function that depends on both I and j. That the function is parametric, so that's learnable, and then I aggregate you can actually show that summation is what you need, right? You don't need anything else. So, well, this is this is message passing. There are higher order architectures, right? Like KGNN, right, equivalent to KWL. So this is equivalent, in the best case, equivalent to WL. It is not equivalent. So the more expressive WL tests, KWL tests, are more expressive than this architecture. But then it doesn't work on pairs of nodes. It considers bigger sets of nodes, right? So whether you to call it message passing or not, you can argue that. So some people argue that you can also think of it as message passing, right? Just with a different graph. In my opinion, it's more a semantic question. I don't know. We never really looked at it. Yeah, I don't have an answer. Yeah.
So it seems like the topological message passing networks and the graph substructure networks both work on the same phenomenon of identifying and counting substructures. So is the expressivity of the topological message passing lower bounded by the expressivity of the graph substructure network?
No, it's slightly different, right? Because subtraction networks, well, first of all, we know their upper bound, so 3WL. Topological message passing depends on what kind of substructures. So they're the kind of side information that you assume is what kind of substructures become cells in this cellular complex. You can actually go beyond two-dimensional cells. You can go to high-dimensional cells. We never tried to go beyond two-dimensional cells. So depending on the choice of these substructures, what becomes a cell, you might have different levels of expressivity. So they're distinct methods. I don't think that they're really comparable.
So something that always confused me about the topological ones is where you glue stuff to structures in the graphs to make them obvious, but can you glue to every structure, or does the structure need to be closed? Because in previous works it was always either cycles or cliques, which are kind of circularly closed.
I think basically the key question is whether it defines a valid cellular complex. I think it should be closed.
I also think it should be closed, but I have no idea about topology.
Yeah, from what I remember, it should be closed. But yeah, so it could be a clique, for example. Whether it could be a path, I don't think so.
So actually, GNNs can count structures that you couldn't glue into or form into a cell complex.
So GNNs can count more general structures, in my opinion. Yeah, so something that doesn't necessarily form a cellular complex.
Okay. Yes. Thank you.
Yep.
In general, I have a question. If we allow more and more nodes, the probability of collision in this representation, do we have any results that it become less or insignificant, or in more general, do this approach extend a bit more into randomized or stochastic versions, so that maybe the guarantee is very low right now from asymptotic point of view, well, secondary run. So the expressiveness theoretical is pretty low, but then if we allow a little bit randomness, then actually it's neural nets.
So you're talking about random graph models, right? Something like stochastic block models.
Yeah,
you can probably analyze what happens to these kind of graphs given certain type of message passing architecture. I've seen papers of this kind. Nothing specific that comes to my mind. Yeah, you can probably, I don't know, compute some probability under the assumption of certain distribution of input random graphs, of distinguishing between them or not. Yep.
So I have a question regarding the size of the graph in practice. We are talking about in terms of maybe not count and edge count. What to say in practice for this KWL?
So KWL doesn't scale well, right? So if it's n to the power k, so also computational complexity versus space complexity, I don't think that you can in practice go beyond 3WL equivalent. Now there are sparse versions of these architectures, so you can do slightly better, but I think they are mostly useful for proving theorems. So basically, because you establish a link to the Weisfer element hierarchy, then you can say that basically, if your network is equivalent to one of these methods, then you know how expressive it is.
Thank you.
Yeah. So there was a paper some time ago claiming that most of the graphs in the most common benchmarks can actually be distinguished by 1WL. Now, I don't know if you read about it. And my question is, now we've seen that even in those cases, more expressive GNNs still get better results. But then what's the reason?
So again, generalization could be one possibility, right? Because you train on one set of graphs and then you test on another set of graphs. Then WL tests in general, they're designed for featureless graphs, right? So they only consider the structure. So how you treat features is also important.
Makes sense. Thanks.
I think we can stop here, and we have like half an hour for coffee break, and then we resume afterwards.
So I will put the slide with the caffeine molecule that everybody likes, and okay. Yeah, basically we stopped at this overview of different more expressive architectures. So let's now talk about, guys, let's start. So basically the situation that we have with the expressive power of graph neural networks, right? So on the one side we have the WL hierarchy, right? So of increasingly more powerful, more expressive graph isomorphism tests, right? And we can find analogies between certain GNN architectures to these tests. On the other hand, the assumption that we are given a graph and we do message passing on this graph might be restrictive in the sense that some graphs are not friendly for message passing. And in this case, typically what you would like to do is to change the graph so that message passing works better. This is a very broad category of methods that are called graph rewiring. So what happens is that you have a gap between theory and practice, right? So the theory, in order to make the link to the WL tests, you need to use exactly the same input graph. The practice tells you that sometimes you don't want to do it. So as always, there is this gap. So if you think maybe take a step back and look at the different types of graph neural network architectures. So the traditional approach in graph neural networks is you're given the input graph, and it's both part of the input and part of the computation, right? Because you use the input graph to send information on it, right? So it's both input and computational object. Now, as we've seen, you can do many different things, right? So you can enrich the graph with some positional or structural features. You can lift it into a higher dimensional topological space, like Simplicia or a cellular complex, right? And do message passing on this object. You can, again, enrich the graph by considering a collection of subgraphs, right? And do maybe some other more exotic type of aggregation that respects the product symmetry group. You can also enrich your representation by considering also the symmetry of the data, right? So these are equivariant GNNs. If I have time, I can talk about it. And then maybe in some special cases, your graph will have special structure like a grid, right? And in this case, you can maybe do more specific choices. For example, you can abandon the local permutation invariance, so you will get back to convolutions. So basically, the common denominator of these approaches is that you have more structure, right? Sometimes you can assume, sometimes you can invent, right? But that's the idea. On the other hand, you can say that you don't like the graph that is given to you, right? And you choose to completely ignore it, right? So you just assume empty edge set, so you're back to the bare bone, right? So the object is just a collection of nodes, which is a set. And these are architectures that are called deep sets or point nets. So that's the simplest case of graph neural networks, right? Where you don't have a graph, you just have the nodes. The other extreme of this is when you allow interaction between every pair of nodes, right? Again, you don't trust your graph for some reason. So every pair of nodes can interact, so it's a complete or a fully connected graph, and this is how transformers work, right? So in this case, you will use, for example, the attentional flavor of the graph neural network architectures, and you will learn the right graph for your task, right? In a sense, through the attention mechanism, for example. There is another class of methods, and this is what we call graph rewiring, where you say, okay, I don't like the graph that is given. I would like to change it a little bit, maybe, and this way the graph will become, in some sense, better for message passing. Okay, we'll talk about it in more details. So let's talk about graph rewiring and specifically about transformers. So in transformers, you assume that the graph is complete, right? So every node is connected to every node. And if you try to apply a convolutional style GNN architecture, right, that depends only on the coefficients of the representing the structure of the graph, then basically here the sum goes over all the nodes, and basically this argument is equal for every node, so it's not informative, right? You're not adding any information. So you need to use at least an attentional architecture, and in this case, this already looks like a transformer. And you can think of attention weights as a kind of learned graph adjacency, right? That depends on the task that you're trying to solve. And this is a special case of GNNs. Now, of course, in natural language processing, many tasks that you want to solve do not require permutation invariance. You actually want them to be not permutation invariance. For example, you want to depend on the order of words in a sentence. So this is typically achieved by adding positional encoding. So in the simplest case, you just equip every node with some additional coordinates that tell you where you are located in the domain, right? Which in case of transformers, it's where you are located in a sequence. And typically, this is how positional encoding looks like, right? So these are just some sinusoids. So for graphs, you can do other things, right? So the analogy of sinusoids would be the, yeah, question?
Sorry, are you aware of some studies about positional encoding, and especially about relative positional encoding, which is getting some popularity in transformers architecture? So, like the studies which consider all invariances in those positional encoding, like we not always want to have absolute positional encoding. Sometimes we want to be. Sometimes some shifts or rotations are not relevant. So do you know some literature on that, perhaps?
Yeah, so yeah, relative positional encoding, yeah, good question. So the analogy, let's say, of the standard global positional encoding would be the Laplacian eigenvectors. So the analogy of local positional encoding would be something that, for example, the DGN architecture implemented, Gabriele Corso and others, directed graph networks. So what they do, they take, for example, the same Laplacian eigenvectors and compute their gradients on the edges, and then transform these features in some way. So this gives you a kind of local directions. So that would be probably a good analogy of local positional encoding. So with Laplacian eigenvectors as well, you have some ambiguities. So there has been actually a recent paper from Derek Lim and others from MIT where they are able to solve these ambiguities. You can use random walk kernels. You can use substructure counting, as we've seen, right? So there are many ways of doing it. But basically, between these two extremes, right, whether ignoring the graph or learning the graph, of course, it comes at the expense of complexity, which is a huge problem in large language models where the size of the domain, right, the length of the text can be very large. So probably one of the key computational questions would be how to compute this attention more efficiently. So here somewhere in between come the graph rewiring approaches, and with graph rewiring, it means that your computational graph is not equal to the input graph. And it's a little bit controversial topic because the graph being part of the input, somehow you don't want to change the input, right? So, but de facto many architectures do it, right? So if you have, for example, a very large graph, like a social network where you have a lot of neighbors in some nodes, you cannot aggregate information from millions of nodes. So you need to sample the neighbors, right? Which means that you are using a different graph from the input one. So neighborhood sampling is a form of graph rewiring, right? You can also use graph neural networks where you bring information from not immediately your one-hop neighbors, but also from multiple hops away, right? So this is also some form of graph rewiring. Transformers are also an extreme form of graph rewiring, right? Where you allow access to all the nodes in the graph. Some kind of pre-processing, right? Where you pre-wire the graph, for example, by some form of diffusion. Yeah, a question?
So how do you do the neighbor sampling? Is it just like a stochastic, or do you have?
Yeah, usually you sample with repetition. So this is what Sage does.
And do you think it's optimal, or is there a way to optimize it in the best way possible?
I don't remember if they looked into it. Probably, of course, it might matter how you sample, but I don't have on top of my mind any significant result that would tell how to do it better.
Okay, thank you.
Could you elaborate more on this diffusion processes on the graphs you mentioned?
Yeah, I will get to it. Yeah, so
Cool.
I will go through the diffusion equations, and then I will.
Okay, cool.
I will talk about this as well. So this is I'm specifically referring to Deagle, the work of Stefan Günnemann and his students. So basically, bottom line is graph is not really any sacrosanct object, and in practice, many architectures, even without admitting it, do some form of graph rewiring. Right, so you can also rewire the graph throughout the neural network, so it doesn't need to stay the same across all layers. And this has been shown efficient, for example, in the context of over squashing, where you can do maybe a few steps of standard message passing and then do message passing on a complete graph, right? So like what transformers do. And so in the argumentation usually is that the first steps capture somehow the structure of the graph, similar to Weisfer and Lemon, and then basically you accumulate this information as features. And there is an extreme example of this. I think it's called Grid. So this is from the group of Phil Torr at Oxford, and they what they do is they use just something similar to heat kernel to encode the local structure of the graph, and then just use MLP. So there are other extremes like this, right? So basically you have just some kind of local feature of the graph that you can maybe make learnable, but then the graph itself is not used, so there is no message passing. And it's I think it's an open question of how much you want to use to capture the structure in the form of features versus in the form of the computational architecture. So the graph can be changed throughout the layers, and well, one of the first architectures to do it was what we did with Justin Solomon and his students. And that was considering problems in computer graphics. So we have a point cloud, let's say, of this airplane. So every point has three-dimensional Euclidean coordinates. And here the task is segmentation. So you want to label each of the points on the airplane, whether they belong to the body, to the engines, to the wings, and so on. And here we create a graph to basically to represent the local structure of the data. And what is shown here by the colors is a distance in the feature space, right, in the latent feature space of respective layers in this network, to the rest of the points from the red point, right? So initially the distance is Euclidean, as you can see that, or that's the input space, three-dimensional R3. But then as you go deeper, you see that it becomes more semantic. So here, for example, points on the engine become closer, or on the wing become closer. So basically the space itself is used for the construction of the graph, and we call it dynamic graph neural networks. So maybe not very lucky name. I think many architectures are called like this. And we use it also in different incarnations or similar ideas under the name of differentiable graph module, where basically you have applications where you don't know the graph a priori. So that's, for example, the case with medical imaging, where you have maybe nodes representing different patients or maybe different regions in the brain. And you have basically two branches of graph neural network architecture, one that is computing the filters on the graph, and another one computing the graph itself. And of course, there is question of computational complexity, but we're able to show that it is better to learn the graph for the task rather than to construct it ad hoc in some kind of handcrafted way. Now, talking about message passing in general, so these are hectically edited slides based on some discussions that I had in the coffee break. So if you think of message passing and different versions of it, like transformers, basically the difference is in two questions: is what information to send, right? What information to pass, and where to pass, right? Whether you follow the graph, right? So whether you pass information to your neighbors, or you pass information to distant nodes, right? Whether it's in k-hop or to all the neighbors in the graph, and the question of what, right, is how you exactly transform your information, right? So it's also interesting to add to this another question is when to send information. And if you look at it, basically it's a multi-step process, right? So this is how a classical message passing neural network works, right? So these are 3 layers of an NPNN or 3 iterations of, let's say, something similar to Weisfeld and Lemon. And I'm sending information from this node to this node, right? So it takes 3 steps. So first here, then these nodes propagate information to their neighbors, and then this green node receives information from both neighbors, right? So in a transformer, all the information is available at once. So at the same moment of time, I'm sending information from all the nodes to the green nodes, right? So it has access to all the information across 3 layers. But you can also, so basically here the difference is where to send information, right? That's the structure of the computational graph. But we don't consider here also when to send this information. And you can imagine an architecture where, for example, you delay the information. So here the first node in first iteration sends information to its neighbor. At the second layer, it sends to 2 hop neighbors, right? So this information becomes gradually available, not like in transformer where you flood all the nodes with information from all other nodes at once. You make it progressive, right? So basically, these are kind of shortcuts that you have in the graph, but they're made progressively as you go deeper into the architecture. You can also make, so you can think of these as a kind of skip connections, but you can also make skip connections sparse in time, so you can delay this information. And I'm saying that here the information from the first node comes to the next node and is delayed in time, right? So it would arrive to it anyway, but it would be entangled with the information in other nodes. So I'm allowing direct access, but I'm delaying it. And this is potentially has interesting implications also on the hardware aspect of graph neural networks, because if your graph is very large, you typically partition it into different parts of memory, right? And the cost of message passing is not the same, right? So messages within the same memory cost much less than messages across different memories. So you can imagine a graph neural network where you are doing fast messages within each part of memory hierarchy and slow messages across, right? So you don't want to wait for all the messages to arrive. You might want to do fast messages while waiting for slow messages, right? So this architecture that we call DREW or NDREW, this version with delays, potentially allows for it. So I think it would be interesting to test it on actually some practical hardware like GraphCore, for example. So let me move to the next topic, and this is physics-inspired graph neural networks. So I promised PDEs, so I need to hold this promise. And let's again take a step back and look at different objects that we've seen so far, right? And also you can argue objects that are studied in this broader field of geometric deep learning. So let's say grids, meshes, and graphs, right? So you can think of them as more or less the same thing, just with more structure, right? So meshes, in addition, have also triangles. So these are simplicial complexes. So graphs with some extra constraints or extra structure. Grids are also special type of graphs where we have certain organization. So if you look at a grid and you look at how you aggregate information from your neighbors, there is no ambiguity, right? In a grid, unlike a general graph, I can order my neighbors in a canonical way, right? I have a top neighbor, I have a left neighbor, bottom and right, like shown here. So it is totally unambiguous, right? So this ordering is fixed. On a mesh, the situation is slightly different. So I can pick up my first neighbor, and then I can order all the rest of the nodes, all the rest of the neighbors in, for example, clockwise orientation. And this is possible because a mesh is a discrete manifold, so it's locally Euclidean. I have this meaningful ordering, right? But of course, the choice of the first neighbor is ambiguous, so I can rotate everything, right? So the ambiguity here is up to rotation. In a graph, as we've seen, any permutation works, right? So everything is defined up to a permutation. So in a sense, graphs have the least structure out of all these objects, right? So second observation is that if I look at grids and meshes, I can think of them as discretizations of some continuous spaces. So a grid is a discretization of a plane, or a mesh is a discretization of a two-dimensional surface or a manifold. We don't have immediately this analogy for graphs, and even though there is an entire field that is called network geometry that tries to think of graphs as some discretization of continuous space, we don't. It would be nice to have some continuous models for GNNs, right? And that's the idea of what we call physics-inspired GNNs. So you can consider some class of graph neural networks as a dynamic system. So you have particles that live in d-dimensional feature space, and let's assume that the dimensionality always is kept the same, right? It doesn't need to be in general graph neural networks. So every node is some point, some particle that moves along a trajectory that is shown by this red line here. So a GNN is essentially a dynamic system, right, that is governed by this system of differential equations. F here is some coupling functions, right, that makes dependency between different particles, and it depends both on the particles and the graph, and it's also parameterized by some trajectory of parameters that are denoted by theta. So t is a continuous time parameter. I can discretize it, and this corresponds to layers of a graph neural network. And the graph, right, you can think of it either as a coupling function, right? So this f here, how different rows of these metrics interact with each other, or discretization of some continuous space, as we'll see in the next few examples. So basically, as the evolution equation, right, that governs the behavior of these particles, I can put here more or less anything, right? So there's plenty of different differential equations that describe different systems, but probably the first thing that comes to your mind when you think of propagation or diffusion of some stuff is the diffusion equation, right? And this, in fact, was one of the earliest mathematically analyzed physical phenomena, right? The diffusion of heat, analyzed by none else than Newton himself in an anonymous paper written in Latin in the Transactions of the Royal Society. So it's interesting, actually, that the journal had a mixture of papers written in English and Latin. And it was anonymous. Well, Newton devised an experimental setup where he heated pieces of different objects, metal, I think, mostly, and then he looked with his self-made thermometer, he measured how much heat is lost over a period of time and devised some law that is formulated in modern terminology like this, what is nowadays called the Newton law of cooling, which says that the temperature that a hot body loses in a given time is proportional to the temperature difference between the object and the environment. He actually didn't use the term temperature, that's modern terminology. He used the term heat, which has a different meaning, or calor in Latin. And somehow everybody guessed that it was his paper, even though he didn't sign it. Now, it took some time until this process was fully understood, so Fourier devised the local version, differential equation that governs heat diffusion, and then Fick in the late 19th century defined what we nowadays understand as diffusion equations. So if you want to apply this idea to a graph, we can consider a diffusion process on a graph. And that's how it looks like. So here x is some quantity that is being diffused. Think of it as temperature if it's scalar. So a node has certain temperature at time t, right? So t is a continuous variable. And what is written here is the self-temperature of the node, right? This is the temperature of the environment, so it's the average of the one-hop neighborhood of the node. And this is the rate of temperature change, right? So, and there might be some proportion coefficient here. So if I rearrange the terms in this expression, I can write it like this, right? So some slightly massaging the formula. What is written here is called the gradient, right? So it's just the difference between endpoints of an edge, right? So I take the feature here and the feature here and subtract them one from another, right? So that's the graph analogy of the standard gradient operator from classical calculus. And what is written here is, again, the discrete analogy of the divergence operator, again, from basic course in calculus. So in terms of operators, you can think of the features as that they live in the nodes of the graph as a scalar field. Then the gradient makes a scalar field into a vector field, right, that lives on the edges of the graph. And then the divergence does the opposite. So it collects the information from the edges that leave that emanate from a node and basically sums them up, maybe with some different weights, right? So that's what the divergence, right? So gradient makes scalar fields into vector fields. Divergence makes vector fields into scalar fields. Acting together, they take a scalar field into a scalar field, the divergence of the gradient or minus divergence of the gradient in our notation is what is called the Laplacian operator, right? So what is written here is the graph Laplacian operator, and by definition you see what it does. So it compares you to your neighborhood, how different you are from the average of your neighbors. And this is really a very important operator. It comes everywhere in mathematical physics, from quantum mechanics to wave equations to diffusion equations, and particularly important here. So what else is the heat equation? So this is very simple, right? So this is what we call homogeneous isotropic diffusion equation. Basically, heat propagates everywhere in the same way, right? What else heat equation is? It's an example of prototypical gradient flow. And gradient flow is a type of evolution equation, differential equation that looks like this. So the step at every point of time is in direction of the minus gradient of some energy that is denoted here by E. And the energy that corresponds to the diffusion equation is what we call the Dirichlet energy. So the Dirichlet energy, you can write it as a quadratic form with respect to the Laplacian operator. And it measures the smoothness of the node features, right? How different you are from your neighbors. So the smallest value it can achieve is 0. And in this case, all the features are the same, right? And you can show that Dirichlet energy decreases along the flow. So if you run the diffusion to infinity, all will become constant, right? So the heat will basically propagate on the domain, and everything will have the same temperature. So this is what we typically call oversmoothing in graph neural networks, right? And I should say that oversmoothing is not necessarily a bad phenomenon. So usually it's described as a kind of catastrophe that happens in GNNs and prevents us from making deep architectures, but it can actually be a very benign thing, right? So you can imagine without any learning. So if I give you a graph and I have labels of a few nodes, and if I assume that the structure of the graph is homophilic in the sense that my neighbors are expected to have labels similar to me, then I can just diffuse this information. So it will be, you can think of it as a heat diffusion equation with boundary conditions. And by just doing this, it is very likely that the result will be very good, right? If the graph is not homophilic, of course, you need to do something else, maybe work harder. But on its own, the oversmoothing is not necessarily bad. Yeah, there is a question.
Actually, I have like 2 questions on this topic. So first of all, can I see this as the, in some sense, the message passing algorithm there, but via the ordinary differential equation between the edges?
Right. So, well, whether to call it message passing or not, I think it's a good question. So every iteration, when you discretize this differential equation, every step will correspond to message passing. Now, in some cases, you can actually have a closed form expression for the solution at any time t, right? This is called the heat kernel. So it will look like the exponential of the Laplacian matrix. So I can compute the value of the temperature at every point instantaneously without doing these micro steps of message passing. So whether to still call it message passing or not, so this is where semantically I disagree with Peter, for example. He still suggests to call it message passing. I think it's not, so I don't know how to call it better, maybe some kind of spatial coupling, right? Because you have direct information to potentially all the nodes in the graph, right? So it is something that doesn't require propagating information explicitly. Right? You might be, when you solve the diffusion equation, especially with it's nonlinear, you might not have a choice. But in some cases, you do. You have closed form expressions, right?
Okay, thank you. And the second question, because I suppose that here is like the mostly ordinary differential equations. Is there any research to introduce some stochasticity there to be, let's say, stochastic differential equations, something like that, and when it could help in this field?
Yeah, so it's interesting. I think there have been some works, and there are some works. So at Oxford, for example, a big expert in this domain is Terry Lyons. So I think they are working on these topics. So we are not considering stochastic differential equations. We are considering whether to call them ODs or PDs. So these are coupled ODs, right? When you discretize a partial differential equation, it becomes a system of coupled ordinary differential equations. I think again here the terminology is more semantic difference. whether you have a continuous spatial coordinate that you want to discretize. So that will be the next part of it. Yep.
Okay, thank you.
Right. Okay, so that was basically the gradient flow, right? And again, an example of the heat diffusion equation as a prototype of the gradient flow. So if you look again at this view on graph neural networks as some kind of evolution equations governing some physical system. So the traditional approach to graph neural networks is to take this differential equation, discretize it, and then parameterize the evolution equation, right? The discrete evolution equation. So every step of an iterative solver here will correspond to a layer, and then you parameterize every layer, right? So that's how you can view graph neural networks. So instead, what we can do, we can start with an energy, parameterize an energy, and then derive the evolution equation as a gradient flow. So apparently there is no difference, right? But the big difference would be that it will allow us to make certain architectural choices. So it will restrict our space of all the possible architectures that we can do here, right? Like, for example, the form of message passing. That will have better interpretability. And of course, I know that interpretability is maybe a bad word in machine learning. So what I mean here is that we will be able to guarantee that certain things happen or not happen. Okay? And I will be more specific in a second. So let's consider the following parametric energy. So we call it generalized Dirichlet energy. It has these two terms. So you can think of it as an energy that a system of particles has. And it's parameterized by two matrices of size d by d, right? D, remind you, that's the dimensionality of the features. So that's the space where the particles move. And we have two terms here. So the external energy term, it acts on all the particles. So think of some force that moves them in some directions. And we have internal energy. So these are the interactions between particles along the edges of the graph, right? Think of maybe colonic interactions, right? Or maybe springs that are attached to some pairs of particles. And we have two types of interactions. So we have attractive interactions, and they happen along the eigenvectors of the matrix W that corresponds to positive eigenvalues, and repulsive interactions that happen along negative eigenvectors. And you can see an example here. So here the space is two-dimensional just for visualization purposes. And the graph here, you see that it's heterophilic. So the colors of the nodes represent the labels. And the positions represent the features, right? The feature coordinates, x and y. So the graph is actually perfectly heterophilic, right? The blue nodes have only red neighbors, and the red nodes have only blue neighbors. And yet we can find directions. So the horizontal direction is repulsive direction, where the particles are separated. And the vertical direction is attractive direction, where the particles cluster together. We can perfectly separate these types of nodes, right? So if my task is node classification on this graph, by this very simple process, I can solve this problem, right? So we will see in a second that this corresponds to a convolutional architecture. By convolutional, I mean that my diffusion operator depends only on the structure of the graph, but not on the features, like in more complicated, for example, attentional networks. So I can write it as AX something, right? So this is what was our distinction. So in convolutional architectures, we had something like this. In attentional architectures, we had something like this, right? So that would be the GCN type of architectures, and this will be the GATT type of architectures. So the fact that this matrix is constant, it depends only on the structure of the graph, is what I call convolutional architectures, right? So, and basically this goes against this folklore that I mentioned in the beginning, that convolutional architectures are not good for heterophilic graphs. So you can see that they can work very well, right? So we need to dive deeper and understand what happens here. So if we write the gradient flow of, question?
Is there a link between this gradient flow and less popular recently this probabilistic graphical method? Especially if you showed the previous slide, it was very similar to restricted Boltzmann, right? When we have this bipartite graph.
Yeah, you can probably interpret it from right. So gradient flows are very basic objects. So it's essentially steepest descent is also a gradient flow, right? So it's a continuous version or variational version of it. Yeah, so probably there are links to many different things. So basically, you're minimizing some energy here, right? So and this energy. So it's not the learning part, right? So it's the the inference, so applying a neural network, minimizes some energy, right? You design the network so it minimizes some energy, right? And the energy is parametric, so what kind of energy to minimize is what you determine based on the task. So that's what is done by backpropagation. So basically, the gradient flow, you just differentiate this energy with respect to its parameters, right? By theta, I denote here these two matrices, omega and W. And one thing that you notice immediately that they all appear in symmetrized form, right? So they appear in quadratic terms, so they appear as omega plus omega transpose. So we can just assume that they are symmetric to start with, right? So that's already first restriction that comes from this assumption of the gradient flow. The second thing is, again, this is by the design of the energy, that the parameters are time independent, right? So they don't depend on t, right, which will become the layer number. And if we discretize it, this is how we discretize. So we replace the temporal derivative with forward difference. So this is what is also called the explicit Euler scheme. So we have some step size tau, and this gives a residual convolutional type GCN again. The convolutional type GNN, why I call it convolutional, because this matrix A, right, that's where the diffusion happens, where the message passing happens, right, when I send information across adjacent nodes, it's not dependent on X, it's fixed, right? So you can call it a kind of a convolution. The weights are symmetric, and the weights are shared across different layers, okay? So the way that you can use it, you can optionally do some nonlinear encoding, typically to reduce the dimensionality. So you have some fixed low dimensional dimension of this space. You apply a linear gradient flow. So all the propagation of information on the graph is linear, so there are no nonlinear activations, right? And then you do some decoder. That's for node classification, right? So that's how the architecture looks like. Now, if you compare it to the classical convolutional architectures like GCN of Kipf and Welling, so there are several differences. So the GCN is non-residual, the weights are non-symmetric, and the weights are different per layer, right? And also they use nonlinear activation for every layer. We don't. So in a sense, it's a kind of antithesis to a typical graph neural network or a typical deep learning architecture. So typically you say that you need many layers, each layer parameterized separately and non-linearly activated. We don't have anything like this here, right? So again, the diffusion part is linear. We have a non-linear decoder and potentially a non-linear encoder. So what we gain from it being gradient flow is interpretability in the following sense, that we can show that in certain situations we can induce both low and high frequency dominated dynamics. I will define it in a second. And what it means is that we can work both with homophilic and heterophilic graphs. Now, because the weights are shared across layers, actually the number of layers becomes a completely irrelevant notion here. So what matters is really the diffusion time. The number of layers is just how finely I discretize my differential equation. And the number of parameters is independent of it, right? Unlike, again, the classical architecture where the more layers you have, the more parameters you have. Yeah, question?
Why don't you stay in the latent space? Why do you need a decoder?
Why do I need a decoder? Well, the decoder can, for example, you might need it to produce a label for a node.
So it's not the decoder in the original space. It could be in any into any.
It could be also decoding the original space, right? So you might, for example, want to work with low-dimensional space, and then the number of your classes might be different, right? But the important part is that it's non-linear, so all the non-linearity goes there. Okay, and well, you can also use an encoder. I will show why encoder can be problematic. We have experimental evidence that it's not needed. So first of all, let's talk about homophilic and heterophilic graphs. So again, homophilic look like this, heterophilic look like this. And the data set here is what we call synthetic core. So it's probably you're all familiar with it. So it's this citation network where we can actually change the structure of the graph in a way that it becomes either more homophilic or more heterophilic, right? And here are the two extreme choices of an architecture. So the task here is node classification. I can either ignore the structure of the graph altogether and do just node-wise predictions with a multi-layer perceptron. And of course, it's not great, right? So it achieves about 67% accuracy. But no matter how homophilic or heterophilic the data set is, the result is the same because it simply ignores the graph, right? The other extreme is a GCN. So when the graph is homophilic, it works extremely well, right? Almost 100%, because when my neighbors contain similar information, I will be basically averaging them, and I will be doing some form of denoising. But when the graph is heterophilic, then it degrades very badly, because in this case, the neighbor information is more detrimental than helpful. So the gradient flow framework, it benefits from, basically it's kind of a mixture of both worlds, so it works as well as GCN in the homophilic case, and as well as node-wise predictions in the heterophilic case, and it gracefully transitions between the two. Now, another important thing, right, and that's where the encoder and decoder question comes into the play. So if you write the output of the neural network after L layers, this is how it looks like. So it's basically it's a polynomial in these matrices. So the matrices are dependent, of course, so there are some powers here. The parameters are shared, but if we ignore the encoder, right, and we can ignore it, at least in the test that we did, basically what the diffusion part can be pre-computed, right? You see that it accesses some kind of powers of the diffusion matrix on the features. So I can pre-diffuse the features once as a pre-computation step, and then it all boils down to node-wise multiplications by these matrices. So the computationally difficult part, both computation in terms of the number of multiplication operations, as well as the memory access, which, unless the graph is very structured, you have random access to your neighbor nodes. This is really the heaviest part of graph neural networks. So these now can be totally trivialized. So we've done the earlier versions of this architecture with just one convolutional layer. We called it Sine. So already several years ago, we tested it on graphs of hundreds of millions of nodes. So with this architecture, actually, because now we also get rid of the nonlinearity, you can apply it to very large graphs. Basically, you can design multi-layer architectures that work well both in homophilic and heterophilic settings. Now, another thing, and this is what I mentioned regarding the nature of the dynamics that is induced by this gradient flow, is if we look at our data, right? And our data, I remind you, it's this the matrix X, right, which is of size n by d. N is the number of nodes, d is the number of dimensions. So we can do an analogy of a two-dimensional Fourier transform, right? I remind you that for a graph that we assumed, an undirected graph, the graph Laplacian has orthogonal eigendecomposition. So its eigenvectors form an orthogonal basis, right? The basis for the rows of the matrix. And the matrix W, which we assumed by virtue of our process being a gradient flow, right? It was symmetric. We can have also an orthogonal eigendecomposition. Let's call its eigenvectors psi and eigenvalues mu. So it forms the orthogonal basis for the columns of this matrix, right? For the dimension d of this matrix. And now in this two-dimensional Fourier basis, right, you can take tensor products of these basis functions of phi and psi. We can write the output of the neural network like this, right? And what you see here is that we have some filter that acts on our signal, right? So this is signal. So these are tensor products, right? So that's the analogy of two-dimensional Fourier transform, sinusoids of sine mx by sine ny, something like this, right? So that's our analogy of this. So this is a filter, and it works both with the frequencies, or the eigenvalues of the graph Laplacian and the matrix W, right? The lambda and mu. And you see that the low frequencies of the graphs are magnified by the positive eigenvalues of W, and conversely, the high frequencies of the graph are magnified by the negative eigenvalues of W. And you can show that if we choose the matrix W in such a way that it has sufficiently negative eigenvalues, then this gradient flow dynamics is high frequency dominant in the sense that the Dirichlet energy, or more correctly, the normalized Dirichlet energy, doesn't converge to zero. So it means that we don't have oversmoothing, right? In the case of oversmoothing, this thing would be going to zero, but here it doesn't, right? So it means that we have some process that doesn't diffuse everything to a constant. It does something more interesting, right? And the condition for it is W having sufficiently large negative eigenvalues. So the analogy of this would be, so if you think of diffusion process as blurring, what we have here is sharpening. And we have both processes at the same time. So the attractive interactions do blurring, the repulsive interactions do sharpening. So we have some directions in the feature space where these processes happen at the same time. Okay, questions? Yep, I think there are many questions, so it was very unclear.
So in these situations where you don't dissipate to a constant value, are you obtaining some sort of chaotic behavior, or are you obtaining either periodic oscillations of?
So this is a symptotic analysis. We don't know. I don't think that I have an answer to your question. It might be that it's so whether we have monotonicity. That's the question. I don't think so, but it might be the case.
So if eigenvalues of W are sufficiently negative, then we can just kind of beat over squashing.
So oversmoothing. No.
Beat over smoothing. And the question is like, is it possible? Does it like, is it hard to do so because there are two dynamics? Is it hard to get those dynamics right? Does it require a lot of hyperparameter tuning or something like this?
So it's a good question. So you can structure the matrix or parameterize the matrix W in such a way that it has two parts, positive eigenvalues and negative eigenvalues. And that's what we do. So basically we help the architecture to have both. And then learning becomes easy. To learn it completely from scratch might be difficult. And we see that GCNs, which are in principle the same architectures, without this restriction often fail to do it.
My question went the same direction, but after the previous answer, I got more confused. So those the matrices, which the delta and the W, they are learned, right? They are not hyperparameters.
W, the elements of the matrix W are learned, right?
Right. So
But the matrix W has constraints, right? So it's, for example, it's symmetric, right? So it has half of the elements of a general matrix W. And then basically by virtue of this theorem, what it suggests us is that we need to further restrict the structure of W, for example, to make it have negative eigenvalues. So typically what we do, we decompose it into a positive symmetric part and a negative symmetric part. And basically this way we guarantee that it has both positive and negative eigenvalues.
Okay, so what is the principal component that makes graph work on heterophilic graphs better than GCNs? And can you somehow update GCNs in a way that they will also work on heterophilic graphs?
So, yeah, so residual connection is a must. We actually show that without residual connection this doesn't happen. Well, the nonlinear activation, I think it's more a complication for the analysis. We don't know how to analyze this. Basically, with this nonlinearity, you cannot regard it as a diffusion equation. Yeah, basically residual connection, and then non-negative eigenvalues. If you remove the nonlinearity, whether if you don't constrain W to have non-negative, or if you don't help the architecture to learn W with negative eigenvalues, you might never be able to learn it. So we've seen this happening as well.
Okay, and what is the role of symmetric matrices W?
So symmetry comes from the assumption of gradient flow. So anything that looks like a gradient flow for this kind of energy must be symmetric.
I see. And what does it mean in terms of operations on your graph, in terms of message passing?
So this is not related to message passing because W is channel mixing matrix. It acts on the features.
I was wondering, what is the relationship? So, for example, you have this gradient flow, and say you want to learn some energy with respect to which you flow. What's the relationship between learning the energy and learning a metric to which with you are computing the gradient? Because if you change the metric, then the way in which you flow is also different, right? Are they equivalent in that learning a metric is equivalent to learning an energy?
Yeah, well, you can think of it indeed in this way, right? So what is the interpretation, physical interpretation of this matrix W? So if you look at the way that Dirichlet energy looks like, right? So it's something like this. So do we use yeah, so let's say continuous version of Dirichlet energy. So it will be the norm of the gradient of x at some coordinate u, let's call it. So u would be the index of the node, right? The continuous version, right? And this is the Dirichlet energy, and let's write it on some domain omega, right? So that would be our continuous version of the Dirichlet energy. Now, what is written here when omega in general is a manifold, a Riemannian manifold? So what is written here is the Riemannian metric of this kind, right? I hope you can see it. So basically, it's inner product defined at the position u, right? And the way that you can write it, so you can write it using Riemannian metric tensor, which is exactly the w, right? So this is something that scales the coordinates of x. Doesn't need to be fixed, by the way. This w, in general, can be position dependent, right, on a Riemannian manifold. So a more general construction would allow w to depend on the position. Maybe not explicitly, because that would be a huge number of parameters that scales with n. Maybe it will be done through some form of attention. So w will, or maybe a positional encoding, right? So w will be a function of positional encoding of the nodes of the graph, right? So there are interesting analogies and potential directions of extending this using, basically this is harmonic energy of an embedding of some manifold, right? Yep.
Thanks.
Yeah, sorry, this will be probably a little bit like far-fetched question, but like in general, like those equations seem to be like kind of similar to what you often get when you analyze like the signal propagation or the type of initializations in deep neural networks, so like the dynamical isometry property. So for example, the requirement for residual connections also appears in there. And like, are you aware like whether there's like any connections between like this work and
potentially? So the closest analogy is neural ODEs, right? Well, these are neural, we like to call them neural PDEs, but they are coupled ODEs, right? So neural ODEs, each row of these matrix will be separate, independent. Here we also have the extra complexities coupling, right?
So like, would you say like that there's something universal in all those?
I'm not sure what do you mean by universal.
Yeah, I'm not sure either, but like it's basically, yeah, it's basically like for example, like this residual rule appears very often in different types of.
So residual rule here comes just from discretization. So that's how you discretize the temporal derivative.
Okay.
You could discretize it differently, so you can use a backward scheme, right? And then it would be implicit. So you will need to solve a linear system to get your next iteration. This actually has been done with diffusion equations. So there are advantages to it because these kind of discretizations are what is called unconditionally stable. But in terms of, well, universality may be not the right term, but basically what we have here in practice is a kind of controlled differential equation, right? So the control is through the parameters W. So they're time independent, but in principle you can think of time dependent trajectory. So you have a controlled PDE that you discretize, and then expressive power becomes a question of, can I reach a certain state of the system, for example, in finite time by choosing the right trajectory, or how far can I be from that state, right? So universal approximation means that in finite time I can reach I can be epsilon close to any state that I want. Generalization, for example, can be probably formulated as some kind of perturbation, right? So I change my initial conditions. I want to see what happens to the system, and there are some results, theoretical results that show that architectural choices, like for example having symmetric matrices, might be crucial for these properties. So I think there is a lot more to explore there.
Okay, thanks.
Okay, so more questions? Yeah. So let's move on with this stuff. So obviously, right. So here the conclusion was that we have no oversmoothing, but we can also consider more interesting equations. So so far we considered very simple isotropic homogeneous diffusion equation. We can also consider non-linear version of the diffusion equation, and this one in particular comes from the domain of image processing, where imagine that you start with an image like this, right? So the portrait of Sir Isaac Newton, that is noisy. So if you run a diffusion equation on an image, it actually has a closed form solution. So it's convolution with the Gaussian kernel, where the variance of the Gaussian is proportional to the time of the diffusion, right? And in the limit, you will have just everything flat, right? So you average all the pixels in the image. You see that you don't want to have a result like this, because it might average out the noise, but it also destroys the discontinuities in the image that for visual perception are very important. So the idea of that was originally by Perrona and Malek in 1990 is to have a nonlinear diffusion equation that is controlled by the gradient of the image, right? So basically, if you're in a smooth region in the image, like here, so you have standard Gaussian kernel, but the moment you reach a discontinuity, you slow down the diffusion. So the effect it has, you don't average pixels of different intensity. So here I'm not averaging dark and white, right? So the kernel will look like this. So it will look one-sided. And it had a lot of different versions, bilateral filters, non-local means filters, and so on. But the idea is always the same. So here, basically, the diffusion speed, right, is inversely proportional to the edge indicator, to the norm of the gradient. And the result that it produces is like this. So this nonlinear diffusion equation knows where to stop locally, and therefore it averages within smooth regions, and it doesn't average across regions. Now we can do the same thing on a graph, obviously. So the analogy would be this, right? So here we have again the gradient, right? This is the divergence, and that's some parametric function that looks suspiciously like a tension, and that's the diffusivity, right? So it's the local strength of the diffusion. And in fact, if we discretize it again with explicit forward Euler scheme, then a particular version of this equation corresponds to the attentional architecture. So this is a GAT. But this was so far. This was continuous time, right? And we wanted continuous space. So right, the original motivation, right, when we compared graphs to other objects, was somehow to have a continuous analogy of the graph neural networks. And if again we look, take a step back and look at how diffusion equations work in the plane, when I discretize the plane as a grid, I don't really have a canonical graph, right? In the sense that there are many ways I can discretize my differential operators, right? So this is how I can discretize the Laplacian on a grid. So I can use neighbors like this, so I can rotate everything by 45 degrees. I can use distant neighbors. I can use convex combination of all these operations, right? Because this is a linear operator. So bottom line, on a grid, I don't have a canonical graph, right? I can actually use a discretization maybe that is different at different points in the grid. Of course, there will be some numerical implications, but the discretization that we choose, right, and as a result, how the nodes are connected and which nodes propagate information to which nodes is to a large extent a numerical convenience, right? What makes sense, for example, from the organization of the memory or the number of nodes and whatever. So we would like somehow to extend this mindset to general graphs. And for this purpose, instead of considering these nonlinear diffusion equations like Perrona and Malek, by the way, they called it anisotropic diffusion, which obviously, if you're familiar with PDEs, it's not anisotropic, it's non-homogeneous, right? Because we have a scalar diffusivity function and isotropic diffusion. We also have direction, so that would be a matrix or a tensor. So instead of considering this nonlinear diffusion equation, we can consider a non-Euclidean diffusion equation. And the model here is the following. That was actually done by my PhD advisor, Ron Kimmel, also in the 90s, about 25 years ago, maybe even more. So again, thinking of an image, you can think of it as an embedded two-dimensional manifold, right? And the embedding is in this joint space where we have a combination of positional coordinates, the x, y coordinates of the pixels, and the feature coordinates. In this case, for example, R, G, and B channels. So a color image is a two-dimensional surface in R5, right? Using this model. Now, by virtue of this embedding, we can define a metric. So we can use the standard pullback mechanism. So in the case of two-dimensional manifold, it's a 2x2 matrix, given like this, right? And we can define a Laplacian with respect to this metric. It's a non-Euclidean analogy of the Laplacian called the Laplace-Beltrami operator. And we can write a diffusion equation with respect to this operator. It's called the Beltrami flow. And we can actually show that it's a gradient flow of a generalization of the Dirichlet energy that is called the Polякov functional. It's used in high energy physics in bosonic strings. Don't ask me what it is, but that's something is described by this energy. So by analogy, we can do something like this on a graph. So now every node in the graph, in addition to having the feature coordinates, also has some positional coordinates, right? So like positional encoding. Ideally, this positional encoding should somehow represent the structure of the graph, right? In the sense that nearby points in this U component of the space should be more likely connected by an edge, right? And the Beltrami flow, basically, it evolves. So we have, again, here parametric diffusivity. It evolves both components, right, that I collectively denote by Z. And the evolution of X component is the standard Fisher diffusion. You can think of the evolution of U as some form of soft graph rewiring, because what I can do, if two nodes become closer in these U coordinates, I can decide to create an edge between them if there is no edge, or if they drift apart, I can decide to cut the edge. So overall, I will facilitate the propagation of information. And I know that it sounds cumbersome, but this is how it will look like. So again, this is the Cora graph. So it has, basically there are three things happening here. So the positions of the circles, right? So circles are nodes. Their positions represent some two-dimensional positional coordinates. The colors represent three-dimensional projection of the features. And you see that both components are evolving, and the graph is also changed on the fly, right? So when the clusters drift apart, then we cut the edges between them. So, right, so it's feature diffusion, positional coordinates are changing, and the graph is rewired. And you can see that the task here is node classification, so there are clearly 7 classes of nodes that we can clearly distinguish here. Now, if you think of it from the standpoint of signal processing, we have a very disturbing picture here, right? So we have a filter that happens on a domain. Yeah, a question?
Maybe before you move to the next one, I was just wondering, because I think what started to appear in the lecture is that you apply some ideas from differential geometry to graphs, and maybe not yet directly, but
not yet, right? So
okay, so we are like talking about metrics and this sort of stuff. So I wonder, maybe you'll be talking about it next. So sorry if I'm pushing it forward, but what do you think are the limits which come from the fact that graphs are basically discrete structures? Like how free are we to apply ideas?
Yeah, give me a few minutes and I will get there. Yeah, so you can find analogies, right? Not everything has exactly a correspondence, right? So, but these analogies, I hope to show that they can be quite useful, right? So, but again, if you look at this picture, so we have some kind of disturbing picture here. So we have a filter on a domain, and the domain is changing under our feet, right? So imagine that you're applying some filter, right, which is what it is, right, the diffusion equation. You can think of it as a form of filter, low-pass filter, and the domain is moving. So I'm doing a filter, and nodes are somehow moving away from me. But this is a very common picture in differential geometry, actually, and it's very common to take a manifold and evolve it under some evolution equation. And typically, when you evolve a manifold, you're interested in what happens to the metric, right? So here's an example of an evolution equation that is called the Ricci flow. So you take the first order the temporal derivative of the metric tensor of the manifold, right, denoted here by G, and you make it equal to the Ricci curvature tensor, right? So basically, the metric evolves proportionally to the local curvature. So it looks very much like the diffusion equation. So here we have temporal derivative. Here we have some second order differential quantity that looks kind of like our Laplacian, right? So structurally, it's similar to the diffusion equation. Of course, what it does is a very different thing. And if you start with this manifold, which has positive curvature on, so this kind of dumbbell, so on the spheres, it has positive curvature, right? And the neck between them, it has negative curvature. So if you run this diffusion, so if you run the Ricci flow backwards in time, what will happen is that this dumbbell become more like an ellipsoid, then more like a sphere, and then will collapse into a point, right? And it was introduced by Richard Hamilton in the 80s with the purpose of proving a famous conjecture in topology that claims that you can characterize spheres by your ability to take a closed curve and collapse it into a point, right? So this is how we characterize two-dimensional sphere. I can take any closed curve on a sphere, and I can evolve it and collapse into a point, right? I cannot do it on a torus. So if I have a torus and I have a curve like this, then no matter what I do, it cannot be collapsed to a point. So the conjecture was that you can characterize higher dimensional spheres in this way, and you obviously heard about it, the Poincaré conjecture, and it was shown by Perelman, actually a slightly more general result, using the mechanism of Ricci flows, right? And that was a breakthrough of the century. It stood open for more than 100 years. Now, what does it have to do with our graphs and graph neural networks? So I remind you that we had this phenomenon, right? That message passing might not be might not work well on some graphs, right? So there might be some phenomena. Some graphs might be unfriendly for message passing, and in particular, it depends both on the structure of the graph and the task. And if my task requires to propagate information from distant nodes, and the structure of the graph is such that the receptive field of the graph neural network grows exponentially fast, right? So the number of the neighbors of the neighbors of the neighbors becomes very large very quickly. This happens in trees. This happens in what is called small world graphs like social networks. Then we have a problem. We have a lot of information that we need to squeeze into a single feature vector. And this is a phenomenon that we call oversquashing. So let's define mathematically what we mean by oversquashing. So let's say that we have a message passing architecture of this form, right? So we have the node itself at layer k, and we have the neighbors. We combine them with some learnable weights. Let's call them W1 and W2. Let's say that the depth of this architecture is L. The width, right? So the internal dimension is P. The non-linearities are well behaved, right? So the Lipschitz continues, and we also have some bound on the weights. So this is what characterizes our architecture. So what is oversquashing? It's some form of insensitivity, right? So if I look at the output of the neural network at node I and I examine how it depends on the input at some distant node j, I can describe the sensitivity of the output to the input through this Jacobian, right? So through the partial derivative. And if the partial derivative is small, it means that the information propagates badly from input to output, right? So basically, I will not perceive the change in the input in the output of that node. And what we show in the paper is that we can bound the Jacobian by constants that depend on the model, right? For example, the number of layers, the regularity of the activation functions, the bound on the weights, and also something that depends on the graph topology, right? And we show in particular, for example, that width does help, of course, at the usual expense of worse generalization, overfitting. Depth doesn't help, for example, and the topology has really the largest effect. And intuitively, we expect that in some kind of benign graphs, like grids, for example, we will not have oversquashing, and in pathological examples like trees, that would be probably the worst case, right? So you see that the topology of the graph comes here through the power of the adjacency matrix, but we don't see exactly how, right? So it's hard to say, right? So what does it mean, a matrix to the power L? So we need something more nuanced. We need some kind of geometric analysis that will allow us to tell apart structures like this and structures like this, right? Something that locally looks like a grid or something that looks like a tree. That's exactly what curvature is designed for, right? So I remind you that in differential geometry, what curvature tells you is that if you take nearby points and shoot geodesics in parallel at the same speed, you can either converge, remain parallel, or diverge, right? And we call these spherical, Euclidean, and hyperbolic geometry, right? So locally it looks like a sphere, like a plane, or like a hyperboloid, or higher dimensional cases as well. So on a graph, the analogy could look like this. So there are several definitions of Ricci type curvature on graphs. So this is a combinatorial definition that we use here. So you can take nodes that are connected by an edge, let's call them P and Q, and look at edges that emanate from these nodes. So if they tend to form triangles, it means that we look at something like a click. If they form rectangles, we look at something like a grid. And if they drift apart and don't form anything, then we look at locally at something that looks like a tree, right? And basically, we can count different types of rectangles, and triangles allow me to skip the details. Basically, for every edge in the graph, we can have this combinatorial quantity that we call the balanced form and curvature. That counts, basically, it looks at a 2-hop neighborhood of an edge. and it counts certain types of rectangles and triangles that surround this edge. Bottom line, it reproduces the continuous behavior. So cliques are positively curved, grids have zero curvature, and trees are negatively curved, right? So that's, I think, to your previous question, how what is the parallel between differential geometry and graphs? So this is an analogy of a curvature. So it's not a discretization of a curvature. It's a discrete curvature that behaves in a similar way. And now the relation between the over-squashing and the curvature, what we show is that if we have strongly negatively curved edges in the graph, then we can write down this bound on the Jacobian, and it means that the over-squashing is caused by the presence of strongly negatively curved edges. Yeah. Yeah. So it's the number of triangles that surround an edge, and this is the number of rectangles. This is the degree. Yeah, doesn't really matter. There are several definitions. So why we call it balanced Forman curvature? Because there is a classical notion of Forman curvature that looks a little bit like this. We just touch it a little bit so it behaves like what is shown here.
But this really relates to the rigid curvature tensor and the formula from metrics. I mean, I don't see it now, but maybe
it's a graph, so you don't have exactly the same thing.
Yeah, obviously, but some, I don't know, components. Can we do some analogy or not? This is something completely new.
So it shows how. So you can think of curvature as how locally the volume changes. So in a sense, it shows how the volume changes. So there are two classical definitions of curvature on graphs, one through optimal transport that is called the Olivier curvature, and this is combinatorial version that is called the Forman curvature.
Yeah, thank you.
Right, so basically the conclusion, well, I should make it explicit that it's strongly negatively curved edges that cause over-squashing, right? So basically due to this bound, actually the presence of negative or slightly negative curvature might be benign. This is what is shown in the expanders paper by Petar Veličković and his co-authors. So these are somehow the optimal graphs, the best for message passing, but expanders need to be slightly negatively curved. So once we know it, we can actually interfere. Basically, we can surgically remove the negatively curved edges and replace them potentially with edges with more positive curvature. And this way, we retouch the graph a little bit, and we show that it improves the performance of graph neural networks both in homophilic and heterophilic settings. So there was a question about diffusion-based rewiring before, and I promised to tell exactly what I mean by this. So this is the paper that is called DIGGLE by Stefan Günnemann and his students from the Technical University of Munich, and DIGGLE stands for Diffusion Improves Graph Learning. So the idea there is that you rewire the graph by basically by computing page rank and embeddings for a personalized page rank embedding for every node, and you connect then in this new embedding space the nodes that are closest. So what it does, essentially, it introduces connections within the same connected component in the graph, right, or within the same clique or cluster in the graph, and it has a hard time to connect across different communities in the graph. So when the graph is homophilic, this is a very good thing to do, right? So you're connecting to similar nodes. But if the graph is heterophilic, it can do more harm than help. And in fact, experiments show that this is the case. They also write it in the paper. The curvature-based approach, first of all, it changes the graph minimally. Here, the change can be dramatic, right? So that's the number of edges that are changed. But it also helps in the heterophilic cases because it's not restricted by this property. You actually typically bridge different communities by the new edges that are created. So still talking about diffusion. Am I actually out of time? Okay. Yeah, so still talking about diffusion equations, here is some more exotic stuff, right? And this is our maybe a bit creative way to illustrate sheaves or bundles. So there has recently been probably a better picture. So that's really sheaves, right, in the literal sense. So what are sheaves? So they actually have very interesting history, and well, I like this kind of historical factoids. So the theory of sheaves in algebraic topology was was introduced by Jean Leray. So he was a French mathematician. He was also an officer in the French army. And when the Nazis invaded France, he was captured and put with his comrades into a concentration camp. And basically, he was asked to work on mathematics. And his expertise was mechanics. So he was very afraid that he would be forced to work on something that would be useful for the Nazis, and basically he will be committing treason, helping the war effort. So when he was offered the possibility to teach something in this camp, he chose a very innocuous topic, algebraic topology, what could be used for. And then after, of course, they were released after the war ended. He published it in a course that was taught in captivity, and one of the papers that came out of this course introduced the theory of sheaves. So sheaves are objects that are taught in algebraic topology. So if we apply them to our setting, to a graph, right, and this is slightly different construction that is called cellular sheaves. So if you think of graphs by analogy to manifolds, so a manifold is a topological space, right? What I mean by topological space roughly is that you have a notion of neighborhood, right? I can tell who my neighbors are, but I don't know. I don't have the notion of distances or angles, right? So if I want to talk about distances or angles, I need some extra machinery. And on manifolds, this is typically achieved by what is called an affine connection, so or parallel transport. So it's a mechanism that tells me how to move vectors between tangent spaces at nearby points, right? I can also define a Riemannian metric, right, if I want to equip a manifold with geometry, and then there is a special type of connection that is called the Levi-Civita connection that is compatible with the metric. So you can think of the same thing on a graph. So a graph is a purely topological object. I have a notion of who my neighbors are, right, but I don't have any geometry. So in order to introduce geometry, I can equip every node and every edge with a vector space, and I can define, by analogy to parallel transport, I can define linear maps. So these are called restriction maps that go between these spaces. So slightly different from manifolds, I go from the space associated with a node to a space associated with an edge. And then if I want to transport information from a node to a node, I need to combine these two maps with one with transpose, right? So basically it's a kind of, right, so I invent geometry on a graph. Right, so I lift it into a more complicated object, and on this object I can now study, for example, what happens if I choose these restriction maps to be of certain class. So these are matrices of certain dimension, and I can choose them, for example, to be symmetric, or I want them to be orthogonal, or I want them to be something else. Right, I can also choose the dimension of these what is called stocks. Right, so these spaces, and I can define differential operators on this structure. Right. So the difference between the standard, for example, gradient and the Sheaf gradient would be the same way as we have on a manifold. I cannot add or subtract 2 points on a manifold. So when I need to subtract 2 vectors, I first need to apply parallel transport. So I need to bring the vector from its vector space to my vector space, to my tangent space. And by doing this, typically I would apply some form of rotation if it's a manifold with the Riemannian metric. And only then I can subtract them, right? So here the same. If before the gradient looked like just difference between endpoints of an edge, here we'll have also some linear transformation that sits in between, right? Long story short, basically I'm interested in Laplacian, right? So I have a Sheaf version of the Laplacian. So it's a block matrix where every block transforms the vectors with these kind of matrices, right? The combination, and now I can apply this operator on my data and run a diffusion equation, and I can run it to infinity with some initial conditions, and I can ask questions like, how many classes can I separate if I choose this sheaf in a certain way? Yeah.
Are you doing graph rewiring here, or are you?
No, we are not doing any graph rewiring. Yeah. So the graph structure is encoded in the structure of the Laplacian. Right. So basically, it's a kind of question about expressive power of this architecture. So I can ask how many classes I can separate, right? So expressive power is slightly different version from the Weisfeld lemon, because in Weisfeld lemon we asked about the types of graphs that we can distinguish. Here we're looking at node level problems.
Can you please make some use cases for this kind of graph and the ones that were showed before, in which the nodes were actually separated with no connections one to another?
So
like which
the graph here is given. So it's, I think, I don't remember what data set it is. Yeah, sorry. What is again the question?
So, like, what kind of what are you trying to model, and why is this configuration better?
Oh, so yeah, the colors represent the classes, the ground truth classes, and the positions represent the features.
And what's the difference between this type and the one in which you do rewiring and each cluster is separated one to another?
So here the features are represented by coordinates. So the closest analogy of this illustration is to the one that I showed with the gradient flow.
Oh, okay.
Right. So the coordinates here represent the features, not the positional coordinates. Right. And the colors represent classes. Okay. So there is no rewiring happening here. You can also potentially use rewiring. And the results, well, I don't want to go through all the results, but basically what we show is that by using different types of sheaves, we can guarantee that we can separate different types of different number of node classes, depending whether the graph is homophilic or heterophilic. For example, we show that you must have non-symmetric relations if you want to deal with heterophilic graphs. Yeah.
So in previous method, WL, it's something like, I think the classification was on top of number of edge, if I get it correctly. Like if you go to the higher classes, then the number of edges also increases. But here in sheaves, is it about the dimension that we have? Like, can we have a fourth dimension sheaves or something like this?
So Weisfer and Lehmann is different. So the hierarchy there is basically there are different algorithms, right? So what they do color refinement for different structures, for a node, for a pair of nodes, for triplets of nodes, and so on. So here we have the choice is what kind of matrices we allow, what class of matrices we allow. So it's typically a group, right? So we say, for example, the most general case is GL, right? So any invertible matrix. Then we can restrict it to be, for example, symmetric matrix. Then we can restrict it to be orthogonal matrix, right? And based on these choices, plus the dimension of the sheaf, we get different results.
So it has two things, dimension and also the matrix.
Exactly.
Thank you.
Yep. So this is a more theoretical question, right? Because it's a good question how we actually know, how we learn the sheaf from the data. But assuming that we knew the sheaf, right? But we allow the sheaf to be only of a certain type, what is in the best case, how many node classes we could separate under different assumptions also about the structure of the graph, whether it's homophilic or heterophilic. Yeah. But basically the bottom line of this story is that diffusion, when you have these extra degrees of freedom, looks more interesting than the standard diffusion on a graph. So the standard diffusion on a graph corresponds to symmetric restrictions with one-dimensional sheaf. Well, so it's slightly more complicated, right? So the analogy of the connection would be the composition of two maps, right? So what we call a transport map. So each of these Fs is called a restriction map, so it goes from node to edge space. They actually can have different dimensions, so they don't need to be the same. The composition, right, so F transpose, is a map from the space of one node to the space of another node. So that's the analogy of parallel transport, right? So when I move a vector from one node to another, I geometrically transform it somehow, rotate it, for example, or scale it. Depends on the class of matrix that I use here. So exactly. So, but then of course in practice you need to somehow to parameterize it, right? So you cannot, of course, in principle you can say that let me learn individual Fs for every edge of the graph, but it's not practically feasible. So in practice, F is a matrix valued function that depends on the node features. So it's a little bit similar to attention. but the tension is scalar. Here it's matrix, so it's a geometric operation. Okay. Any questions? Right. So basically, to summarize this part, so what do we gain from this physics-inspired perspective on graph neural networks? So first of all, I think it's different viewpoint on old problems like oversmoothing, bottlenecks. It allows to, on the one hand, to interpret existing architectures like GATS, for example, from a different perspective. It allows to potentially design new architectures, right? For example, using, if you think of a GNN as a discretization of differential equations, then of course you can ask what kind of solver can I use? Can I use some more interesting things with adaptive step size or maybe, I don't know, multi-grid solvers and so on. It allows to make principled architectural choices, right? Like with example with gradient flow. So basically from the gradient flow we get restriction on symmetric weights, we get residual connection. We can also have some theoretical guarantees, right? Again, like we've seen with the gradient flow, but maybe also of other types like convergence, stability, and so on and so forth. But probably more interesting are links to other fields that are less explored in graph neural network literature, like in particular differential geometry or algebraic topology. And of course, diffusion is just one example of evolution equations. You can consider more interesting things. So this is one example, right? So probably have seen these kind of things. Coupled oscillators, so the metronomes that are put on a table, and because the vibrations transfer from one to another, initially they might be oscillating out of phase and then they become synchronized. So think of something like this, but on a graph. So the coupling occurs on a graph in a learnable way, and depending on the task that we want to do, we want somehow to interact between these different oscillators. So it's also a differential equation, but it also has a second order kinetic term. So unlike a diffusion equation, it has also oscillatory component. And here we show, for example, that we can probably avoid oversmoothing by using this type of equations. How much time do I have?
Up to 15 minutes, maybe 10.
15 minutes. Okay, so what I would like to do, if in 15 minutes, let's talk about grids. So I definitely ran out of time because out of all the geometric objects at the end, well, we spent all the time on graphs. I think grids also deserve their little bit. And probably, well, everybody is familiar with grids, right? So let's look at them maybe again from the perspective of geometric deep learning and hopefully some new intuition, or at least for some of you, if you have not seen it before. So, and this also relates to the previous question of why we call graph convolutional networks convolutional. So first of all, a grid is a graph, right? So it's a particular type of a graph. But for simplicity, I would like to assume that the grid has periodic boundary conditions. So basically, it's what is called the ring graph. And the idea of geometric deep learning, right? This group-based framework. We had some domain, and we had a group that acted on the domain. We had a signal that was defined on the domain. So this is a general type of this mechanism that is often called lifting. So now I have a linear operator, so this can be anything, right? So this can be a non-linear complicated thing. Here I have a linear operator, so the group representation that acts on functions defined on the domain, okay? And in the case of a grid, this is just the shift operator. So this is what I show in one dimension. So it just cyclically moves the elements of the vector. Now, another thing that you see in a grid is that it has a fixed neighborhood structure, right? In this example, every node is connected to exactly 2 neighbors, and they are also ordered, right? So I always have the one before and the one after. In a 2-dimensional grid, I might have some partial order, right? So I have something on top and something on the bottom. So in the past, on a general graph, we had this kind of aggregation function, right? So we have the feature of the node itself, and then we had a multiset that was unordered of the nearby features. And because we didn't have any order in this multiset, the only thing that we could do is to apply a symmetric function, apply a permutation invariant function. Now we have a different situation. Now the nodes are ordered, right? So we have a fixed order of xi minus 1, xi, and xi plus 1. So this function can be more general, right? So it doesn't need to be symmetric. And if this function is linear, then we get the convolution, right? And if I write it as a matrix vector product, then it looks like this. So it's a special matrix which has fixed elements along the diagonal, right? So this is the local weight sharing that we have in convolutional neural networks. So this is a special type of matrices. They are called circulant matrices, right, or convolutions. So it's synonym. You take a vector of parameters, right? Let's call it theta, and you create this matrix by cyclically shifting by one position this vector of parameters and appending it as columns. And that's how you get this matrix. Again, I'm assuming periodic boundary conditions. So technically speaking, it's not a convolution. It's a circle convolution or a cyclic convolution, but just to make things simpler. Okay. Now, first thing that you learn in Algebra 101 is that matrix multiplication is not commutative, right? AB is not equal to BA. But with these matrices, with convolutions or with circulant matrices, that's not the case. It's actually a special type of matrices that do commute, right? And in particular, they commute with one of them, which is the shift operator, right? So a shift is also a circulant matrix, right? Or also a convolution, right? So looks like this. So what does it mean that that a convolution commutes with a shift? So this is what we call shift equivariance, right? So in other words, I can first apply convolution and then shift, or I can first apply shift and then convolution. The result will be the same, right? So convolution is shift equivariant. You can show the other way around, right? So you can show that if you have shift equivariant linear operation, so I take a matrix and I tell you that it's shift equivariant, you can show that it must be a convolution, right? So basically, convolution emerges from considerations of translational symmetry, right? So the only linear operation that is shift equivariant is convolution. So convolution is the only thing that satisfies this property. And we've seen again this geometric deep learning blueprint, so allow me to show it again. So we have a grid, we have the translation group, its representation is the shift operator. So the convolution is a function that is equivariant with respect to this group. Now we also know that there is an intimate relation between the Fourier transform and the convolution, right? And let's actually try to understand what the Fourier transform is, where it comes from. So we know from algebra again that commuting matrices are jointly diagonalizable. It means that they have the same eigenvectors, or more correct, eigenspaces. But here we assume that the multiplicity of eigenvalues is trivial, so they actually have the same eigenvectors, and they only different eigenvalues, right? So all commutative matrices satisfy this property. So if I have a set of matrices that commute pairwisely, then this is the case, right? And this is the case for convolutions or for circulant matrices. So we can pick up one of these matrices, right, and compute its eigenvectors, right? And we know that all of them will have the same. And it's convenient to look at the shift operator, right, at the matrix S. And if we compute the eigenvectors of the shift operator, you can do it by hand. It's actually not difficult. You see that they look like these complex exponentials. So this is exactly the Fourier transform, or more correctly, the discrete Fourier transform. So the question, of course, that remains is what the eigenvalues are, right? So we know that the eigenvectors of all convolutions are the discrete Fourier transform, so these complex sinusoids. But the eigenvalues, also you can show it, are the Fourier transform of the vector theta that forms each of these matrices. And this gives us this dual relationship between the Fourier transform and the convolution. So if I have a signal x, I can do convolution in the spatial domain by multiplying by a circulant matrix, or I can do it in the Fourier domain. I can compute the Fourier transform, and there the Fourier transform diagonalizes the convolution, so it becomes an element-wise product, right? So basically, the product of two Fourier transforms is the Fourier transform of the convolution, right? And typically, in signal processing, the filters are already designed in the Fourier domain. This is bread and butter of signal processing. So the advantage of using the Fourier transform, because this operation usually on grids can be done efficiently. So instead of n squared operations as you would typically require here, because the Fourier transform, the matrix has a very redundant structure, you can avoid these explicit multiplications. You can reuse some of the multiplications and do it in n log n operations. So there are classes of algorithms that are called fast Fourier transforms. And this is from the approximately the 60s when this was derived. The most famous algorithm is by Cooley and Tukey. This is how signal processing has been done, and you have it everywhere, from your stereo to your iPhone, from your computer. So this is how it's done. You cannot do it on graphs, because on graphs, the analogy of the Fourier transform would be the eigenvectors of either the adjacency matrix or the Laplacian matrix. So if they are symmetric, they have orthogonal eigendecomposition. But these matrices do not have these redundant structures. So the Fourier transform has n squared complexity. It's dense matrix multiplication. Actually, some of the early graph neural network architectures came from this domain of signal processing on graphs, where that used the eigenvectors of the Laplacian or the adjacency matrix as an analogy of the Fourier transform. So the difference in the case of in the Euclidean case on a grid, there is no difference between the two, right? So the Laplacian is also obviously a circulant operator, circulant matrix, and so is the shift, right, or the adjacency matrix of the ring graph, which happens to be the shift operator. They all commute, so they have the same eigenvectors. On the general graph, they are different. So therefore, these methods slightly differ. So the way to think of why you want to look at the adjacency matrix is this, right? So this is how you can think of your convolution. So this basically it's multiple diagonal matrix. Now you can write it as a sum weighted by these coefficients of the powers of the adjacency matrix, right? So the adjacency matrix of the ring graph will look like this. So this red diagonal, right? So that's the shift operator. So if you take a square, you will get this. If you get cube, you will get this, right? So you combine all of them, you will get this general convolution. So first architectures that try to do learning on graphs looked exactly at this, taking powers of either the Laplacian or the adjacency matrix, basically polynomial with learnable coefficients. Now, if you also look in terms of the degrees of freedom, so a fully connected layer will look like this, right? So it has no symmetry. So here the symmetry is trivial. So it has n squared degrees of freedom. In the case of convolution, so the symmetry here is translation. We have order of n degrees of freedom, right? So we reduce dramatically the number of parameters in the neural network. We reuse the same coefficients everywhere. In the case of a graph, because we have permutation invariance, we don't have the order of the neighbors, so we must use the same coefficients. So we can only distinguish between ourselves and our neighborhood, right? So that's, well, here it's, I'm assuming, a complete graph, so this will look like something like deep sets, for example. So, but the number of parameters is order of 1. So it's independent on the size of the domain. What else can I say? Can I tell you? Well, I know that I'm out of time. So do you want to hear about molecules, or you heard about molecules? Okay. So let's talk about molecules. I promise that I will try to do it fast, and probably heard in Miguel's lecture as well. So I will probably be a little bit repetitive. So graphs are a very convenient model for molecules, right? Basically, a molecule looks like this, so you can represent it as a graph, and maybe that's not how chemists think of molecules, but at least in some applications, graph neural networks have been successful in predicting certain properties of molecules that are required for virtual drug screening, right? Where the space of potentially synthesizable drug-like molecules is huge, something like 10 to the power 60. The number of molecules that they can actually test in the lab is significantly smaller. So you need to breach this by some kind of computational methods, and graph neural networks have been shown, again, in predicting some properties to be significantly faster, while similar complexity to similar accuracy to classical methods. So one thing that is important to say in regard regarding molecules. So molecules are not just any graph where the symmetry that we have is the symmetry of the domain, right? The permutation of the nodes or the reordering of the atoms, right? So the domain symmetry tells you that no matter how you order the atoms in the molecule, I still want to be able to say that it's the same molecule. But it also has geometric coordinates, right? So in addition to the, let's say, atom types that we have here, I also have the XYZ coordinates for every atom, right? So it's a graph that lives in a continuous Euclidean space. So here what I want to say that if I rotate the molecule, for example, or translate it, I want to be able to say that the properties remain the same. So in this case, typically you look at the special Euclidean group, so rotations and translations without reflections. Reflections can actually change the properties of molecules, or you can use some other groups as well. And there have been already several interesting success stories. So one of them was a group of Jim Collins at MIT. So they used graph neural networks in virtual screening pipelines where they tried to determine which compounds could be used as new antibiotics against antibiotic-resistant bacteria. And they famously found that a candidate drug that was tested against diabetes called halicin was actually effective across a broad range of antibiotic-resistant bacteria. But in the things that we are doing, we are mostly interested in proteins. And this is, well, I think this is in general, proteins are important targets for drugs because they are involved practically in anything that happens in our body, from defense against pathogens, right? Antibodies are special types of proteins, to delivering oxygen to our cells. Hemoglobin is also a special type of protein. So basically they're everywhere and they're encoded in our DNA, so we don't know any life form that is not based on proteins, or at least for the time being. And it was conjectured in the 70s by Anfinsen, a Nobel laureate in chemistry, that you can determine the structure of the protein from its sequence. So proteins are long chains of amino acids connected to each other, and then under the influence of electrostatic forces, they fold into these complicated structures. But we are interested in the opposite problem, so maybe a little bit incorrectly we can call it some kind of inverse problem. So I would like to design a protein that will fold into a certain structure. Of course, it's not that simple, because it is tempting to think that we have a sequence that then folds into a structure, and this structure endows the protein with certain function, for example, what kind of molecules it binds. And initially, computer scientists look at proteins as sequences because, well, it's just strings, so we can look for certain patterns. You can try to align different sequences together, right, like multiple sequence alignment. Then came the problem of structure prediction, and that's where AlphaFold excelled recently. But then the problem of function is distinct, and you can find examples of, for example, proteins with different sequences but similar structure. You can find proteins with very similar sequences but very different structure, or you can also find proteins with different sequences and different structures but similar function. So they happen to bind the same molecule. So a good analogy here is this lock and key metaphor that was introduced by, I like quotes from Nobel laureates. So that was from Emil Fischer, also Nobel laureate in chemistry. So he was talking about enzymes, but I think it's more general, applies to proteins broadly. So same way as you have a unique key that fits into a lock, you might have a unique molecule, or at least that's the wishful thinking, is that a unique molecule that will fit into some pocket that exists on the surface of this folded protein structure. And this is how drugs are typically designed, right? So you have a protein that is your target, so that's how its surface looks like. And here is some small molecule that sticks into this hole and binds this molecule, and that's how the drug works. So this is actually a molecule, well, not exactly of caffeine, but of a compound from the same class, and that's how it binds the adenosine receptor in the brain. Many other interesting targets, though, they don't have these kind of pocket-like structures, and there are interesting systems of proteins interacting with each other, like this one, the program death complex, where you have two proteins called PD1 and PDL1, and they are involved in cancer immunotherapy. Basically, these proteins tell our immune system not to kill healthy cells, and some cancers have these proteins, so they manage to evade the normal functioning of the immune system, and the idea is to block one of these proteins, either PD-1 or PD-L1, and this way, basically, the malignant cells are destroyed by the immune system. So you need to design some binder that will bind to one of these proteins, and they happen to have these kind of flat interfaces, so they're considered to be hard or impossible to drug by small molecules, but you can drug them by proteins. So that's the idea of biological drugs, where the drug itself is a protein molecule, typically an antibody for a variety of reasons. So you can use geometric deep learning, well, and unfortunately I didn't have time to talk about it, but basically instead of considering graphs, we can consider surfaces. So we model proteins as manifolds, as basically the external surface that appears to the other molecule that tries to bind it, and this way you abstract all the internal intricacies of the fold. So let me try to show you an example. So this is a plastic model of a protein. You see, so this is protein is the one that the person holds is supposed to bind to this transparent one. So you see that these complicated helixes and other things inside. So that's the protein fold. But what appears from the outside is this transparent surface. So this guy doesn't care what happens inside. So it cares only about the structure. Of course, the problem is more complicated because the conformation of the protein, its geometric structure, might change as a result of the interaction, but at least it's in some cases it's a good approximation. So long story short, we can do special type of neural networks that operate on these surfaces, so they take into account both geometric and chemical properties of the molecular surface, and they try to find complementary structures that are expected to interact. So think of kind of pieces of three-dimensional puzzle, but it's not only geometric complementarity, it's also chemical complementarity. So they need to have the right charges so they don't repel each other. And this is a method that we called Massif. So we were lucky to appear on the cover of Nature Methods in 2020. And this year we also had a paper in Nature that contained experimental results. So we also hope to appear on the cover, but they chose a different one. But because we paid for the cover, here you need to see it. I think it was a cool image. So we used this method to design new binders for different targets, and basically it's a fragment-based design. So we use this neural network architecture to identify potentially complementary targets that then we use to build the binder. And here the experimental results show different structures. So here's a binder for the PD-L1 oncological target, and we also have the crystal structures. And here's an example of another binder for the SARS-CoV-2 spike protein. So that's the virus, coronavirus that caused the COVID-19 pandemic that has been terrorizing us for more than 3 years now. And basically this structure binds the region of the spike protein that interacts with the ACE2 receptor of the host. So that's how the virus enters into our body. And here we also tested it. So we have the structure from cryo-EM. We also tested it on different variants of the virus. So the alpha, beta, and omicron, that probably everybody was following in the newspapers. So you see that it binds many of these, maybe some others less. And here is also a comparison to a clinically approved drug. So that was antibodies that were developed by AstraZeneca. So basically what is shown here is how much inhibition you have versus concentration. So the smaller concentration, the better, of course. So we are not as good as the AstraZeneca drug, but still it's something that was designed totally computationally, and this is actually a pseudovirus neutralization. So it is probably much closer to real validation than at least anything that myself as a computer scientist could think of. Well, I think I will probably stop here, but if you think of diffusion models, right, so generative models everybody is now talking about, right, like the DALI 2, and now of course you have way better results. So you could imagine something like this for molecular design. So you have some condition on let's say diffusion model that we use here, like the geometric structure of the target pocket, and you try to build a molecule that satisfies these constraints. So you don't really have a text prompt, but you have maybe some other way of conditioning the model. So so this is one example, maybe not very interesting. So another example is what we call diffusion linker, where we have small molecular fragments, what is called pharmacophores, that you know how they bind the target, but you also need to connect them into bigger molecule, and we try to basically to start with these little fragments and to diffuse the linking structure that connects them. We're not very lucky in publishing this paper in Europe, so we'll probably send it to some chemical journal. Well, I think I will stop here. Sorry for running out of time. Thank you very much.
Yeah, we are over time, but if you have still a couple of questions, if not, you can ask individually maybe. I'm not saying. Okay, but thank you again for the amazing talk. Well,
thank you.